going to turn this one off. I'm going to try to speak from this this microphone. So I want to join Dave in thanking everybody for coming to this. I'm going to do just a very brief introduction, and then we're going to jump into the program because there's quite a bit to cover this afternoon. I would like to introduce my colleague, Matt Malika, who many of you have probably interacted with, sitting back on the table. So if you need anything, Matt or I will be happy to help you. My name's Todd Bryan, and I work for the Keystone Center, which is a nonprofit organization in Colorado. We got involved in this project last fall with Lowell Observatory. Very quickly got the city of Flagstaff involved in it, and have kind of built the planning committee from that. I'll say a little bit more about that tomorrow. I wanted to just really start out with by introducing the presenters for this afternoon session, and then we'll cover a lot more of the program tomorrow. We have three presenters this afternoon, James Benya, Deborah Burnett, and Chris Lugenbuehl. I just want to say a little bit about each one of them, and then I'll just turn it over to Jim. Jim Benya is the principal of Benya Burnett Consultancy. Jim's a professional engineer and lighting designer with 40 years of experience in architectural lighting design, including daylight, theatrical, and performing lighting, urban streetscapes, light as art, and zero-net energy building design. Jim is also the author of 2 books, Lighting Design, Basics and Retrofitting and Relighting, and is among the most widely respected international lecturers and speakers in the field of lighting design, daylight lighting design, and efficient buildings. Together with lead author Deborah Burnett, Jim will be authoring his 3rd Wiley publication entitled Evidence-Based Lighting Design, tentatively scheduled for release late in 2014. I think it's towards the end of August, so you guys getting busy on that, right after the conference. Okay. Deborah Burnett is also a principal with Benya Burnett Consultancy. Deborah is a nationally recognized health and wellness design authority and Keystone speaker who has appeared on HGTV as well as national and worldwide TV and television and radio. Recognized an authority in the field of epigenic design. Deborah is an award-winning interior designer, building contractor, and chair of the Color Marketing Group. Combining her knowledge with interior environment and evidence-based scientific research, Deborah bridges the gap between public health and design with her unique design perspective and extensive health research, where she focuses on how and why human health, genetic expression, sleep, workplace fatigue, cognition, obesity, and aging are affected by light, color, temperature, music, and sound. She's a member of the American Society of Sleep Medicine and is a frequent presenter at professional conferences. And finally, Chris Lugenbuehl. Chris, where are you? Chris is back here. Okay. Chris Lugenbuehl is an astronomer at the United States Naval Observatory Flagstaff Station, where he has worked on a variety of photometric and I'm going to hope I get this word right, astrometric projects since beginning work there as a summer student in 1981. His research has involved star-forming regions, young stars, and transient phenomena such as gamma-ray bursters and optical transients. He is also a lover of the natural night. For over 25 years, he has been actively involved in light pollution issues, seeking to preserve the highest quality dark skies through education and research. His efforts focus on not only research to improve our understanding of how light pollution is produced and how it may be limited, but also education to raise awareness of our light-obsessed and environmentally isolated culture, of the cultural, scientific, and human value of natural light, and not just for astronomers. He is a co-founding member of the Flagstaff Dark Skies Coalition, a nonprofit organization that coordinates and enhances the world-leading sky protection efforts of Flagstaff. And also every 2 years, Chris and the coalition coordinate the production of Night Visions, an international fine art exhibit that celebrates the beauty and wonder of dark, star-filled night and the inestimable value it brings to human life and culture. The program this afternoon is titled Dark Skies, Good Nights, and it's really focused on very much the basics. So we're happy that you all regardless of your level of knowledge of this area, have agreed to attend this afternoon. So I will go ahead and turn it over to Jim, and he'll take it from there.
Good afternoon, everyone, and thank you for coming. This is really great. And it's an honor to be here with this program. I want to thank Todd and Matt and everybody else for allowing me to be a part of this program and for making me a part of the committee that helped plan all this. And there's other committee members that you'll get to meet over the course of the next couple of days who were vitally responsible, especially my good friend Liz, at making sure that this was a really good program. When we conceived today's program, the idea was that people are going to be coming from all walks of life. Some of you are working in public administration, facilities management, who knows what all of you might be doing. But I know that we all don't always speak the same language when we talk about lighting. I also serve on the board of directors of the International Dark Sky Association, and I'm the chairman of the technical committee. So it's our responsibility to try and be looking out what's going to happen, what can we do to establish standards that will make for ever better control of lighting and in turn be able to deliver the type of quality that Chris will be talking about here as well. So my role in this is to orchestrate today. I will be presenting along with our other two presenters. We've got a little bit of a schedule. Let's see if I can get rid of that thing here. We've got kind of a tight schedule, but one of the first things I want to say is our overarching goal of this entire program, as we planned it, is to tackle the forces that are causing us to lose that night sky. And they're not going backwards, and they're not going down. They're going up, and they continue to go up. How can we reverse that trend, protect the resources that are already fairly well preserved here? That's one of the goals that's the goal as we all get together. And I wanted to just make that point. Along with it, though, come a few other things. Along with it come, let's see if this thing works, reducing wasted energy, because the light that goes up in the sky is wasted. The energy that generated it is wasted. We can deal with the high cost of maintenance. Lighting systems, the more lights you put in, the more money cities spend powering them and fixing them. And much of that is wasted too. The loss of the night sky beauty and awe, and I loved Chris's introduction and many of the things that he had to say about it. The disruption of the circadian cycles of all living beings, and that's Deborah's expertise. She's going to be speaking here in just a minute. But I wanted you to all know that our job here today is to give you as many facts as we can. We're going to try our very, very best not to try and give you our personal preferences, our personal observations, or our personal leanings, but rather give you the facts, because the next 2 days is all about us talking together and coming up with plans that we're all part of, and not just one of us or two of us. So in the first 25 minutes, Deborah's going to talk about light, the environment, its impact on human health, and all the other living beings, and a lot of other stuff. After she's done, Chris will step up. Chris is going to talk about the physics of light, the atmosphere, sky glow, how we measure it, and what we do about it. He's one of the world's acclaimed experts in this, and I'm very glad he can do that. After that, we'll take a 15-minute break. If you have questions, we're going to save as much time as we can at the very end for Q&A. If there's a lot of questions as these folks finish, when we come back after the break, we may tackle a few of those before I get into the rest of the program, which is going to be a whole lot of that lighting terminology and common language for us all. So without further ado, I'm going to introduce, I got to do a little computer jiggle here. I'm going to introduce my partner and my best friend and my wife, Deborah Burnett, who is going to be speaking about, well, I'll let you tell them, because that's really your expertise. Let me get this thing started for you. Here we go. Here you go.
Thank you. As Jim had said, I'm very, very excited to be able to present this information to such a diverse crowd. And that's the primary reason why I am presenting my information, my study, my research, and my work in this area, because I speak a number of languages. I speak scientific, medical, as well as practical and everyday. And that's what it's going to take, someone to be able to take the information from knowledge and apply it to practice. From bench, the scientific studies and peer review papers, and apply it to bedside. How we're going to use it in our everyday lives, in our homes, on our streets, and in our city governments. How are we going to make wise decisions for our citizens? How are we going to protect not only the citizenry, but all life forms that fall within our jurisdiction? So today I'm going to be sharing with you almost 20 years worth of my research, and I know that Todd had said that I was once on television. That's been a lifetime ago, many pounds and a lifetime ago, I'm afraid to say. But since then, I've been doing a number of projects and working with governments as well as organizations and a number of hospitals here and internationally, and working with the medical community to help them better understand the connection of the environment and how it impacts sleep, obesity, cognition, fibromyalgia, and a number of other conditions and behaviors. And so for the next 23 minutes, I'm going to be bringing some information to you about how light impacts more than just the visual system and our visual acuity. We have to understand that we have an environmental connection. We've been gifted with a living body, a living brain that literally is connected, hardwired to receive information from the environment, and for two main purposes, for energy management and for survival. And it's because of energy management that was the key goal in our evolutionary history. Everything was about conserving energy and allowing the organism to be able to thrive in whatever environment he, she, or it found itself living in. We have a circadian system. And please don't be confused. Circadian system is different than circadian rhythm. I know so many times in the media we're sometimes guilty of saying, oh yeah, the circadian rhythm does this, this, and this. It's not just about the circadian rhythm. The circadian system is all inclusive. Every one of our trillions of cells in our body and brain has a component that directly links it back to the circadian system. And the circadian system is comprised of many different facets. It's circannual, in other words, everything that happens at least once a year. And in like birds and fish, it has to do with nesting and plants, germination. Infradian, that's something that happens less than once a year, but a little bit, thank you, more than every 24 hours. A woman's menstrual cycle is a good example. Circadian, something that happens with a regular, consistent history every 24 hours. And you have to keep that in mind. It's actually 24.2 to 6 hours, the circadian rhythm. And it has to be aligned with the Earth, the rotation of the Earth, about every 24 hours. So the circadian system has to be aligned or attrained with, again, those same environmental conditions to be able to allow the different chemical components of our body and brain to be able to synchronize with the environment that we're in. And we have ultradian rhythms, those rhythms that are naturally occurring that are going to happen less than 24 hours. We can use that as our nasal dilation. How many of those have you realized that we have two nostrils and they don't operate at the same time? It operates on an automatic system about every 2.5 hours, and that's to prevent us from basically overloading our body on cellular waste. And we have sleep cycles that occur 90 to 110 minutes each cycle. These are ultradian rhythms, and all of this has to be coordinated and it has to be managed, and that's the job of the circadian system, to keep us within our energy management and to keep us surviving until we reach obsolescence and then depart. And we have a photosynthetic system because we're not the only ones who inhabit this earth. We have a light-dependent cycle, and that's based for energy management again, for light harvesting. Basically, it's a solar collector. Every time you have a leaf, it's like a giant solar collector. And energy conservation of the plant, the organism itself. And then we have a light-independent cycle. It's commonly called a dark cycle. And this is for cellular respiration and for fixation of CO2. And without a rest period, and we don't, at one time we used to think that plants sleep. Well, they don't sleep, but they go through a different process that involves their respiration and the fixation of the CO2. And then we have something on a good portion of our plants, particularly the legumes, the pea family. That form of plant that is now going to be considered to be the major source of protein here on our planet as we reach 8 billion people. And it's a nicotinic system. And this system basically means that at night, the leaves will draw up. And it has specific organelles in the cellular structure of the plant itself that allows for the moisture and respiration to occur. Now, the thing that we have to also realize is that between the circadian system and the photosynthetic system, we have a specific molecule, and that's our energy currency. It's called adenosine triphosphate, ATP, and it is involved in all life forms here on this planet. And ATP is something that is also light reactive. In science, our researchers haven't found too much information yet, but it's now the coming thing, the coming area for future discovery. And that's the whole purpose of this whole entire class today, to be able to share with you some of the basics, let you know about some of the information that's coming down the pike, and so that you can make an informed decision based on everything that you learn here today and throughout the rest of the conference. Now, the thing before I go into any detail about the circadian system, these are the basics that Chris Lugenball and Jim were going to be detailing later this afternoon, is the energy of light itself. It's the spectral distribution of light. We know that the electromagnetic spectrum, there's a thin area in the air in the center of it that we call the visible radiant energy. And this is where we have most of our circadian impacts are pretty much contained within this visible band. It extends out to the ultraviolet and also to the infrared. But for our purposes right now, we're just going to be dealing with the visible spectrum. And here's another way of just showing the differences. The short wavelength energy, I know some of you had asked me when I was introducing myself to a few of you, what does short wavelength or blue wavelength energy have to do? It is an alerting mechanism to most living organisms. It's short wavelength light. Long wavelength light basically has a longer wavelength. It's a difference in frequency and amplitude than it is compared to the blue wavelength, and Jim will go into detail about this. And plants, they have an action spectrum. In other words, they are going to be optimally productful to be able to have their energy conserved and managed well and wisely, and to be able to produce what it is that that particular species of plant is doing, from short wavelength to red, primarily in the red and the blue spectrum area. And it's because of the chemicals. The chemicals that are involved in photosynthetic process also have a footprint and respond to different wavelengths of light. We have chlorophyll A, primarily in the short wavelengths, as well as chlorophyll A again here in the long wavelengths. And we have a number of other chemicals that are involved, and they each have a signature or an action spectra of how they're impacted whenever light that falls within these bands are impacting their living conditions. Now, for humans, we also have chemicals. This is just a few of the chemicals that have a relationship to the visible spectrum as well as into the UV spectrum. Elastin, flavins, which are responsible for blood pressure and the size and diameter of our blood vessels. We have different neurochemicals. Melatonin, serotonin are all responsive. They have an action spectrum. In other words, they respond optimally whenever they are under different wavelengths of light as found in the natural daylight, or now we know under different artificial or electric light sources. These same chemical reactions occur. For vision, Clarissa Luginbull is going to be speaking about the photopic and scotopic way that our eyes respond differently to different wavelengths of light. And you have to keep in mind that just because we have 3 visual cone receptors and rod receptors, not all living beings have 3. Actually, 80% of women, we're now shown that we have a 4th visual receptor. Bees, they have 3, but their optimal range, their wavelength sweet spot, if you would, is different than humans, as is pigeons, honeybees, starlings, pigeons, starlings, and we have honeybees here. They all respond differently to wavelengths of light. And our electric light sources now, they cover the gamut. So it's not just about selecting a luminaire based on the aesthetics of the luminaire or what we perceive to be a warm white or a cool white. We have to go further. We have to look into the spectral power distribution to really understand what the light is consisted of and how it's going to impact any living being that's within that distribution of light. We also have a slide that I was proud to introduce on the international level, and this is from the International Dark Sky Association, and I introduced this slide in Berlin when I presented the keynote there in 2009. This slide represents everything in the gray area, is the area that's pretty much confined for circadian, the primary circadian input, in other words, when it's present and when it's absent. That's going to give the major cue for circadian response. The hash line is also showing the area of the spectrum from 400 to about 630 nanometers that is going to produce a circadian response. So if we have a street light that has a high percentage of 550, 600, 603 wavelength, we're still going to be getting a circadian impact. Now, the solid black line here represents the traditional and typical LED light that first came out when the Chinese started importing the LED lights here to the United States. It has gotten a little better, but primarily most of the LED lighting that we see fall within that range. We can also, if we overlay a true spectral power distribution or a visual graphic, you can see how the spike right here for the LED mimics exactly the circadian sensitivity. And that's fine for daylight, for daytime exposure, but what happens when we're providing blue-rich white light at night when we're not supposed to be experiencing that? So this is some of the quandaries that we face. And selecting lighting is not just about what color it appears, 8000K, 2700K. We have to understand it's about spectral power distribution, and every light source has a spectral power distribution or a footprint. So I'm going to ask everyone, what distribution do you feel is represented here with this nighttime image? Is it blue rich? Is it red rich? How would you determine that? Now come on, let's see.
Understand what the imager sensitivity is first.
Okay, understanding the image sensitivity. That sounds plausible, but unfortunately not the right answer to get you that Cupid doll. Okay. Most designers would say that, it's a blue-rich white light source. So yeah, let's put something with a blue-rich white light in there. Well, if we're looking at what the true spectral distribution power of moonlight is, it's predominantly long red wavelength. So we can't even trust our own eyes or our preconceived perception of what light is. We have to look at the spectral power distribution. So, with that basics in mind, let's look at the human connection to light. We are gifted to receive, react, and to anticipate our surroundings. And we do that very uniquely. Not just to our species, but to all species have different variants of this. We have a sensory system to receive the environmental information. Vision, rods, cones, hearing, smell, taste, pain receptors. We also have a genetic system. And this system is designed specifically to react with the changing environment, and it's now recognized and called the epigenetic system, E-P-I-G-E-N-E-T-I-C, above the gene. And basically this came about, it's the study of change, it came about in the late 1990s when we realized that the brain has what's called neuroplasticity, the ability to change based on the environment. 51% of our genes are now determined to be regulatory genes subject to epigenetic control. A good portion of our circadian genes, genes that Dr. Stevens will be speaking about on Tuesday, as it relates to disease prevention and formation, how this literally is going to be impacted by the environment of temperature, food intake, and primarily about light. And we also have a system to anticipate. Just like a football player, when the quarterback throws that ball, he doesn't throw it at the guy running over here, he throws it where the guy's going to be. That's what the circadian system does. So if the circadian system receives information from light, its primary source of information, that blue light, daytime, great. I get blue light at night, well, I guess it's still daytime. This is when we're throwing in the monkey wrench. And the circadian system, it's not just about getting up and going to sleep. It's about a circadian rhythm, yes, an endogenous rhythm. That's 24.2 to 24.6 hours that has to be reset or realigned with the Earth at least twice a day, called a chrono or crossover. And it's determined by light and temperature. But the circadian system is responsible for everything that we know to be human. Wound healing, immune response, muscle coordination, hormonal regulation. Muscle coordination. Anybody here work out? We now know that our muscles also have circadian clocks. And it's optimal to work out your lower body between 5 and 7 in the morning. Upper body between 5 and 7 in the evening. Because our muscles have different clocks. Even our red blood cells have a circadian clock in it. Every organ has a different clock, and they all speak to a master clock. The circadian system has been around for 600 million years in one form or another. From the time that we are 28 weeks in gestation as a human, we have a fully operational circadian system that has to be reset after the birthing process that then fully completes its cycle by the age of 6 months. But by the age of 8 weeks to 11 weeks, it's already receptive to the environmental light directly through the abdominal wall, the placenta, and into the baby itself. Circadian rhythm, again, this is an endogenous rhythm, it's inherent rhythm. 24 hours, the earth, it has to realign, so it has to be reset. And the sleep-wake cycle, it's willed behavior here in humans, and it's a restorative process that basically helps us to be able to, one of the component thoughts right now, is to be able to get our synapses, the way that our brain responds with our electric impulses and we be able to make connections. By the end of the day, the synapse or the cleft opens up and becomes wider. One of the thoughts of why the sleep process is so vital to our ability to perform and to produce the next day and to remember things is that the sleep process brings that cleft back closer together and it makes it easier for us to make those vital neuronal connections. And it does it with what's called a feedback system. Let me give you an example. Melatonin is a hormone that's involved in the circadian rhythm, disease, progression, initiation, and also melatonin is involved, obviously, in the sleep-wake cycle. And melatonin has to be squelched, or it has to be basically taken down to the bottom level during the daylight hours only. It has to be the expression level that's circulating has to be reduced. And at night, it has to have dark conditions to be expressed. And again, I'm using non-scientific terms to make sure that everyone is very aware of what we're going on. And it's an inverse rhythm. It's to provide homeostatic balance, an equal balance within the body and brain. And adenosine is key ingredient of making all of this work. Remember that ATP, both in photosynthetic system and circadian system, it's extremely responsible here as well. Hormones, melatonin, cortisol, ghrelin, neurotransmitters, they all are responsive to the circadian system. The circadian system, photosynthetic system, responds to light, not just moonlight and sunlight, but we now know electric light, daytime electric light, natural day lighting as we call it, and light at night. And what happens is the body is receiving the information as wavelengths of light, spectral power distribution. It's coming in through the eye, and the eye is then taking this information and transporting it through the brain. And when it's taking the transportation, particularly if it's going for circadian entrainment, it's taking it through a very specific pathway called the retinohypothalamic tract, and it's using that light as a dosing protocol, just like we do a drug. For the spectral distribution, the timing, is that light coming during the day or night? How bright is the light? What location? Is it coming from up here or is it coming from down low? We now know that if light coming from above is going to be striking an area of the eye that may not be as impactful on the circadian system. So there's some ways to be able to trick that system. Prior light history, how much time we spent during the day prior to trying to sleep at night. And the source of that light, how intense is that light, and the composition of the light itself. And the light goes directly for circadian entrainment. Right here is where the master biological clock is located. Light, for visual purposes, goes a circuitous route, several different synoptic area steps, back to the visual system, and up to the parietal lobe right here, where we eventually go, oh yeah, guy in the orange coral shirt. That's visual response. So, we're looking at vision again, front of the eye, back of the eye, the retina. And right in through here, we have what was discovered in the late to mid-1990s, and then the rest of the world fully recognized and accepted, a new visual system for non-visual system. So it's vision because it's in the eye, but we have to remember it's non-visual photoreceptors. Traditional vision, the information comes in, hits the back of the retina wall, goes through 3 to 5 different layers, and then comes back through the optic nerve as translated as wavelengths of energy, information, and then goes through the steps to the occipital lobe for vision. For the circadian impact, they're called the IPRG cells, intrinsic photosensitive retinal ganglial cells, and only 1 to 4% of all of our ganglial cells are comprised of this unique subset of cells. And it is going specifically to the master biological clock, which is located right here, and it's a one-stop shop. It's a highway. It's located in the hypothalamus, and it literally is also tied in through an indirect route to the norepinephrine system of the body. It's called the Edinger-Westphalia connection for the pupillary light reflex. So every time your pupil blinks, or you are in a car and a bright headlight comes and you go like this, that is also impacting your circadian system and the ability for melatonin to be produced, to circulate, or to be expressed or silenced. Now, this is just a very simplistic graphic, but this is representative of the Earth and the different colors that we perceive, the light as it changes throughout a 24-hour period. And something's paying attention. The genes, particularly 2 key genes by the name of clock and BMAL1. These genes pay attention with epigenetic regulation, then send information to the circadian system, which then operates with the circadian rhythm to unify and align. The circadian rhythm then sends the signaling out to every cell in the body to be able to produce hormones primarily at night, neurotransmitters during the day. These in turn set out another set of genetic responses that then set off additional genes to be turned on and off that are fed back again and reinforced through circadian system and through the light that it receives, where we can sleep and wake. And we now know that electric light does the exact same thing. Circadian desynchronization, a very, very hot topic right now in medicine and scientific research, because every one of these diseases, including breast cancer, are now known to have desynchronization ties, links directly to circadian desynchronization. In other words, your circadian system, your circadian rhythm, your sleep-wake cycle are not aligned with what nature intended. 1.5 million new cases of breast cancer. World Health Organization in 2007 actually issued a number 2 causation of cancer, working the night shift, again, because of circadian desynchronization, and warned specifically about it. Here in the United States, the American Medical Association had an unbelievable and unprecedented policy change, Policy H-135-937, specifically targeting this range of light. And at that time, its potential carcinogenic effects relating to the melatonin suppression, breast cancer, obesity, diabetes, depression, mood disorders, and the list goes on and on and on. And what it was referring to, lights from our television, our alarm clocks, our design of using blue light at night, the quick markets where you run in and you're employed to work the night shift. Lights coming from above in our nighttime environment, cell phones, tablets, aquariums, book lights, LED lights. These are all impacting our circadian system. And it's not just humans. Sundial Bridge in Sacramento. In 2005, it regularly had 15,000 Winter Run Chinook Run coming underneath the bridge on its way for spawning. After the bridge was illuminated, 2011, we now have 824. It's because of predation and circadian desynchronization for the fish. Same thing is happening with our bats, because the lights at night are particularly harmful to the bats' migration patterns. And this is some of the information that I've gleaned in placing together the information for the Wiley publication book that hopefully will be coming out in the next few months, that we have to understand that we're not alone here on this planet. Light is the primary Zeitgeber or controlling mechanism for not just our existence and our survival and our energy management, but for all life forms. So I know we have just a few minutes of questions, and then we're going to be turning it back over to... Okay, 2 questions, I'm told. Yes, question.
Somebody blind from birth.
Yes, yes, with eyeballs.
Or no eyeballs.
Oh, with no eyeballs. Yes, we have 2 problems there. And that has been wonderfully addressed by a colleague, a friend of mine, Dr. Steve Lockley, and Victoria Reinold, and Steve's at Harvard right now, and he did some of the major information and research on this, that if you have eyeballs, you literally have an intake or an intact circadian system. Without eyeballs, or a fake, you basically have a free-running system, and you are unfortunately resigned to have issues with sleep, with productivity, performance, and other problems throughout your life. And so you have to do a number of other things, including drug management. But it's a very strong area of research that springboarded into everything that we now know about the circadian system.
So the tie is still there.
Yes, it is. It's because the cells on the lower portion, the inferior section of the eye, the IPRG cells, they receive the light directly. They literally do not have to go back through the process of hitting the back wall, the retina, and then coming back through the bipolar, the amacrine, and the other layers. They are hit directly, and the chromophore is melanopsin, whereas in the back of the eye is iridopsin and rhodopsin. So it's a different type of chemical itself, and it's a direct highway path to the master biological clock. One other question. Yes?
Do you know the color temperature that the AMA policy H, the blue light, where it tends to be a problem? Is there an identified color temperature?
It was a wonderful paper that was fielded by Bud Brainer and Richard Stevens, who's going to be speaking here on Tuesday, and 4 other well-known and well-respected, including Dave Blask, who I know personally and had the wonderful opportunity to be there when he unveiled the connection of melatonin light at night to breast cancer. And it was their work, and it's about a 50-page white paper that is referenced to, let's see if I can go back, this. And so if you would like to be able, right here, to literally just Google the report for the Council on Science and Public Health, you would be able to see. They mentioned some, but they're not lighting scientists, and so they were very generic in their suggestion that it's short wavelength light, and they gave a range. And right now, Bud and some of the others who literally identified the primary range from 465 to about 479 or 480 nanometer. And we now know that through the work of Samar Hatta, who's out of Johns Hopkins, who's doing the research on the rods, we now know that the rods and the 600 to 630, also have impact on the circadian system.
Just one more quick question.
Okay.
Take one more quick one.
Okay, thank you. Yes, night lights for children. That's something that the AMA has addressed, and they are recommending, as is a number of other research and professionals, that it be red wavelength light, not amber, but red. And we can see that in studies from nursing homes and in nurseries, in terms of nursing homes for ameliorating some of the Alzheimer's problems that are associated with sleep fragmentation, with the dependence on sleep meds and memory recall. Red wavelength light for children most optimally.
Okay, thank you. We will have more. Thank you, Deborah. There will be more opportunities for you to talk to Deborah directly, and we'll have some open Q&As a little bit later. We got a lot of material to get through. Next, I'm going to ask Chris Luganbuehl to come up. Chris is going to tackle a very complex but very important part of what we all have to deal with here, which is dealing with artificial sky glow. And if there's probably nobody in the world who knows more about this problem and how to deal with it than Chris. So let me see. Chris, you want to go ahead and launch your program here? I'll let you take over. Thanks. And use whichever mic. Just make sure you use the mic. Because we're recording.
Just a moment. All right, can I have the light then, please? So you can see the slides and not me. So I'm going to jump a little bit more narrow than Deborah just covered and talk somewhere in between about the more focused topic of just the impact of the lighting use on sky glow and its impact on humans and on astronomical instrumentation. And I'm going to get a little bit more nitty-gritty and actually talk about some kinds of lamps as well and how their impacts vary on these processes of producing sky glow. Is this as dark as we go? A quick summary is I'm going to talk briefly about what causes sky glow. I'm going to talk under some people's feet, and I apologize, and I'm probably going to talk over some people's head completely out of the room to some of us like me. I apologize ahead, and I hope it's understandable to most. We're going to talk about receptors in the eye, which Deborah has mentioned a bit already, and how their spectral responses are and how that relates to vision. It turns out that the spectral response depends very much on the brightness level of what you're looking at. So we're going to talk a little bit about the brightness levels that you experience in your life, primarily in the nighttime environment, but I'll talk briefly about all environments. Finally, we'll focus a bit on different types of lamps, their spectra, and how they interact with this visual system differently because of their different spectra. We'll talk about how they affect sky glow, we'll talk about how they affect star visibility a bit, and the spectral width, which I'll explain when I get near the end. And then finally, we're going to talk about why it looks like And I think the answer to that is, why did I leave that little piece on my slide without deleting it? So what is sky glow? I think probably most of us in this room have some idea what it is. Lots of light of different kinds comes from the sky. Starlight is not what we think of as sky glow. Starlight or sunlight or moonlight are not what we think of as sky glow. What I mean to focus on is the light which comes from the atmosphere itself, not from celestial objects beyond. That light coming from the atmosphere can originate in the atmosphere, so-called natural sky glow or air glow. We won't talk about that too much. We're going to talk about, I think, what you all expected us to talk about, and that is sky glow arising from artificial light sources. Hi, Seth. You can see that I'm going to focus primarily on the effects of sky glow on dark, clear night skies. Even though this photograph shows you a little bit, I think you can see on the right side there's some clouds, and that's a very important topic, the interaction of clouds with sky glow and its ability to reflect light back to the ground. That's not a topic I'm going to talk about today, though. And I don't think it's a topic much of the conference, although you can understand that clouds, in a way, can be an amplifier of the amount of light that we let go up. The clouds will report even more of it to the ground than you might get from the atmospheric processes that cause artificial sky glow that I'll talk about. So, what causes sky glow? We use light at night on the ground, and even after it illuminates the surfaces that we light to use and to be able to see, such as roadways or parking lots, some of it reflects up into the sky. Light also can get into the sky directly from fixtures that are either primarily used to light the ground but inadvertently light the sky as well, so-called unshielded or poorly shielded fixtures. But some fixtures may be directed upward for various reasons, like lights at the bottom of billboards or lights to floodlight the sides of buildings or flags. Both of this light still is headed out away from us and into space. Most of it goes that way and never comes back. But a small amount of it interacts with the atmosphere, the molecules and particles in the atmosphere, and is reflected or scattered back toward the ground to cause what we're talking about here, artificial sky glow. I'm going to talk about two different ways of perceiving the sky glow, two different human activities that might be impacted by this artificial light. First, we're going to talk about its impact on all of us, the people, anybody who looks upward with their eye, either the naked eye or with their eye behind something like a binocular or a telescope. That's what I mean by using the eye. We're also going to look briefly at its impact on instrumentation. Primarily, I'm going to focus on astronomy, and that's going to be very brief at the end, but also cameras like you have for taking that picture you saw on the previous slide of the night sky, even though cameras are sort of a little bit meant to act like eyes, so they're not quite the same as astronomical instrumentation. First, let's focus on the visual sky glow, that is sky glow perceived by eyes. The remarkable thing to keep in mind that's going to lead us to some interesting conclusions here is that our eyes function naturally and without assistance over a stupendously wide range of brightness. 10 million to 1 between the daytime environment and a starlit environment. And although you don't see the same things in those two circumstances, you can see in those two circumstances, 10 million to 1. Also, there's an intermediate level, natural or artificial lighting at night. How do we accomplish that? The simple thing that almost all of us can see and tend to think of when you think of adaptation to bright or dark levels is the change in the size of the pupil of your eye. That's something we can all see. You don't need instrumentation or chemical labs to find it. But that only gives you about 10 to 1. We still have 1,000,000 to go. That's where the interesting stuff starts to happen, when we accomplish that 1,000,000 to 1. And it turns out that the way we do that leads to different spectral responses in these different lighting levels. We're sensitive to different wavelengths in these different brightness levels. This is pretty simple. An eyeball, we know that light comes in through the front of the eye, is refracted by the lens in the cornea of the eye to focus on the back of the eye. Deborah briefly covered this already. And at the back of the eye is where we detect that light and convert the nerve signals through the retinal cells into something we call vision. Looking at the retina in detail, the light comes to a focus in a layer called the retina, which has rods and cones, also which Deborah mentioned briefly. The important part to recognize here is this: we're starting to get into this area of what explains this 1,000,000 to 1 ability to adapt to different levels of brightness. The cone cells are what we use in daytime environments. We're using those here in this room. There are many of them in our retina, particularly toward the center of our field of view, the center of where you think you're looking or where you are looking when you look at somebody's face. There are 3 different kinds of them at least. Apparently some people have 4 that I just learned tonight or today. They are sensitive to different portions of the spectrum, but overall they have a certain range of wavelength they can see. The rod cells, also mentioned, are the ones we use at night, but there's only one kind of rod cell. They're sensitive to much fainter levels of light. If we look at the whole range of wavelengths that we can perceive, the whole range of what we think of as visible light, and I've extended this a little broader than maybe many would do, from 350 to 700 nanometers, not all colors are perceived equally. If we look at the sensitivity, or as Deborah called it, the action spectrum of the different kinds of cells, the photopic response in light is the response of all of those kinds of cone cells working together. There's 3 kinds, but on an average, working them together, they come up with a response like that. Thank you, Jim. There are 3 kinds of them. That means that you can see, some of them will see red more and some of them will see blue more, and your brain uses that information to tell you what color the object you're looking at is. Its peak sensitivity is around 550 nanometers. That's the light you are most sensitive to, but you can see anywhere between 450 and 650 nanometers, and those are that's the light spectral response of daytime or photopic vision. Scotopic or dark vision uses the rod cells. They have a response that looks like this. It looks similar in shape to the photopic response, but it's shifted towards the blue. Its peak is around 500 nanometers, about 50 nanometers bluer, and it goes between about 400 and 600 nanometers in terms of the wavelengths of light it can see. So example, photopic light can see deep red light, but at nighttime and using your rods, you can't see red light very well. The important issue to recognize here is that there's only one kind of rod cell. So if there's more violet light at night, or if there's more green light at night, as long as the light level is low and you're just using the rods to look at it, your rods won't tell you whether there's more green or whether there's more blue, and it looks black and white to you. You've all seen that in a moonlit environment or even starlit environment. You can see things, you can't tell their color generally. Now we're going to look. The important part to realize is that these 2 bright and dark receptor systems respond in different lighting levels. So let's look at the range of brightness levels in our environment. Let's quantify a little bit what I had in that first graph with the daytime, nighttime, daylight, starlight, and parking lot illumination levels. In the lighting business, we call this luminance, or for common everyday speech, we could just call it brightness. It's measured in something called candela per square meter. You don't need to know what those units are. All you need to know is that the brightest ones are way up there on the right side. That's daytime. About 100 times fainter is what you might use in your office. Still easy to see. Another 100 times fainter, you're talking about the brightness levels of roadways. And then finally, not quite another 100 times fainter, you're looking at a moonlit landscape. What kind of cells are we using for these 3 ranges before I get to starlight? It turns out that the brighter levels, we're all using 100% cones. We have good color vision. We're using those light receptor cells that can tell us what color things are, but they only operate in the brighter levels, including office lighting. And actually quite a bit fainter, as you can see, even to less than 1/10 of the lighting levels in offices. Doesn't quite reach street lighting levels, though. The rods, on the other hand, the ones that are sensitive to very faint light, don't reach that level. They operate in an area I haven't covered yet. I'm going to get there. In fact, I'm going to spend most of my time there. But meanwhile, we have rods operating at the very faint level. In the middle, we have both rods and cones operating in some mix. So for street lighting and moonlight, we're using a mixture of rod perception and cone perception. So for example, under street lighting, you can see colors. Your cones are still operating. Under moonlight, if you have really bright colors, you can see colors under moonlight. But as you get fainter, the cones are switching off, and slowly it's only rods. How bright is the nighttime sky? Let's look at the next slide here, which is an image, a fisheye image of the sky over Lake Mead, taken by the National Park Service Night Sky Team. This is an artificial color. You wouldn't see color like this. This is just the way that we display it to help you see the range and brightness more easily. The darkest part of the sky at the very top, very zenith of the sky, straight overhead, is about 0.0002 or 0.2 of a millicandela per square meter. We'll put that on the graph in a minute so you get to see where it lies in the brightness range. The brighter part, when you move into the light dome of the city, and by the way, I meant to describe this, this is the sky overhead Lake Mead, and the light dome you see on the right-hand side of the image is the light dome from Las Vegas. As you start to look into that light dome, you get up to much brighter levels. Here we have 3 millicandela per square meter, and it gets brighter than that if you look right down into the core of the city light dome. So moving back to this graph, you see that range of brightness falls purely in the scotopic range. And you may say, well, what about light pollution? When it gets light polluted, don't you start to get into a little bit of mesopic? Don't the cones start to work? As an example, I have measurements from West Lockwood, I think might be in the audience here, taken at Lowell Observatory and also by the Park Service folks, taken at Lowell Observatory, just a scant mile from this location, showing the brightness range at Mars Hill, and this is where it lies right there. That's certainly a light polluted site. It's nowhere near cone vision or mesopic vision. So even at a pretty light polluted site, you are looking at a sky using just your rods, just black and white vision. So the relative sensitivity of the spectra of these two kinds of cells really matters for looking at the sky. When you're looking at the night sky, you're using rods. So we need to pay attention to what the spectral response is, and that's going to become important to looking at the light pollution impacts of different kinds of lights that we use outdoors. This is a picture taken by Richard Wainscoat from Mauna Kea. Towards on the far distant horizon there, Honolulu. This is on the Big Island, Hawaii. That's the lights in the deer grounder on the Big Island, and in the far distance is Honolulu. We use high pressure sodium very widely around the world, particularly in the US. We also use metal halide lighting for sports lighting, but also for roadway parking lot lighting in some areas. Some areas use low pressure sodium, and increasingly we're seeing a lot of interest in LEDs. These are the kinds of lights we're going to look at. Primarily, not going to discuss the issues of safety and security and such, and how these have other impacts on their ability to see and operationally for the lighting area that you're actually lighting and what you're lighting it for. That will be discussed in the coming days. I'm going to focus on what is the impact of these different spectra of light on the ability to see stars, on the ability to produce sky glow. Moving back to that spectrum of visible light from 350 to 700 and the photopic light curve, you can see that high pressure sodium, the most common light, is an interesting light. It has it's a pretty spectrum, I think. Most light comes out in the yellow and a little bit green. It looks like it's not quite optimum. It's not in the most sensitive area for daytime vision, but it's not far from the most sensitive area. It doesn't have much blue. Metal halide, on the other hand, covers the whole range of what you can see with cone vision, daytime vision, or parking lot lighting vision. You can see all the colors. It's well represented. It covers everything. It's good for lighting up products. It's good for lighting up this room. Low pressure sodium is kind of like high pressure sodium, only more so. Now we don't have so much green or blue. In fact, we have hardly any green or blue. Almost all of it comes out at that location in the yellow, which is not quite at the peak of the sensitivity of the daytime vision or the parking lot vision, but not far from it. I will sometimes as well talk about, besides low pressure sodium, something I'll call an ALED or an amber LED. I know that's kind of my abbreviation. There's different kinds of amber LEDs, but we're just going to call an amber LED one that looks very much like low pressure sodium. It looks just like that, except it's missing that faint green line. LED is similar to metal halide. The usual white, high color temperature LED covers the whole range, the whole gamut of colors that you can see with daytime vision. The filtered LED, which we'll also sometime, I'll be discussing further on here, is a product developed by someone who else is in the room here, sitting in the back row. It starts with a white LED, but puts a filter in front of it that blocks out most of the emission below 500 nanometers. So you can see that one also covers the range of colors that you can see in daytime vision, cone vision. But we're going to be looking at the light coming back from the sky, which I've shown is much fainter. So we're going to be more interested in the scotopic response. Now you can see that for metal halide and LED, we're still covering everything that scotopic vision can see. All the colors that you can see are there. And even the FLED covers a little more than half of the spectrum of what you can see. There's some impact. You've lost some of the efficiency at stimulating nighttime vision with the FLED, but it still works pretty well. But HPS and LPS, something different is happening. We didn't change their wavelengths, but we're no longer at night very sensitive to their light. Over there at 600 or 590 nanometers, if you trace that bright area down, I don't know if you can see an arrow, yeah. Does that show up on your screen? Yep. Whoop. I went forward. You can see that that wavelength is hardly even sensitive down here. The scotopic curve is almost down to zero. That's going to turn out to be very important. Now I've kind of jumped over something a little bit. I've been looking at the spectra of lamps, and I've been telling you, well, that's what you're going to see coming out of the sky. I want to take a quick detour, and then I'll come right back to here to say that, well, it doesn't actually go from the lamp into your eye. You don't call that sky glow. You call that lighting. So what we do is I'm going to look at what happens to that light, how it gets off the light fixture, hits the ground or doesn't hit the ground, gets into the sky, scatters off the atmosphere, and comes back. Does that affect what's going on here? There have been a number of models that have been evaluated and published in papers in the last couple of years by myself and by others, which have looked at this problem. We've looked at the brightness of the sky caused by lighting sources on the ground at a variety of distances from 100 meters to 300 kilometers away from the source. What we see, first off, is something a little bit confusing, or actually something that's really common sense if you think about it, and that is, if you look at this graph, which shows distance across the bottom from 100 meters on the left side to 300 kilometers on the right in a logarithmic scale, and vertically brightness of the light coming from the sky. This is not brightness to the eye, this is brightness measured with a meter. The interesting thing is right off you see that it drops off dramatically with distance, and that shouldn't be any surprise. If it's a unit of 0.1 when you're 100 meters away from it, it falls to less than 1/10 of that by the time you get a kilometer away. There's an interesting thing happening here, however. We know that the sky in the daytime, or this picture of the nighttime with moonlight, is blue. That leads to the idea that the light that's going through the atmosphere there, moonlight or daylight, the sunlight in the daytime, is white. It's all colors. So why does blue come back? That's because the atmosphere tends to scatter toward the ground more of the blue than the other colors. So is that going to affect what happens with our artificial light as well? If you go back to this graph, you can see that actually it is happening. I've looked at the analysis here for 3 different wavelengths, blue, yellow, and red, and you can see nearby more blue is coming back than red. But when it gets fainter, I can't see what's happening. So what I'm going to do is I'm going to take a ratio of everybody to yellow, and that way I can look at down there at 1 kilometer or 10 kilometers, how much more blue compared to the yellow is coming. And that will take out this main variation of brightness with distance. This is what it looks like. So again, we see that nearby there's more blue coming back than the red portion compared to the yellow. And that remains true out to about 10 kilometers. After that, blue actually gets fainter, and red gets brighter compared to the yellow, almost backwards. But anyway, forget that. Nearby, it is kind of what we expected. But the interesting thing is it's much, much smaller than people initially thought when they thought of this problem. They thought Rayleigh scattering, the scattering coming from molecules, I'm sorry to use the word Rayleigh and drop it on you like a brick, but it's the scattering from molecules, the light going up, hitting molecules and coming back. That kind of scattering tends to be very blue. People thought that might be as much as 120% brighter for blue light. But in fact, it's at maximum 15% variation from red to blue. So basically, the light that goes up from the ground is the same light, the same color that comes back as long as you're within about 10 kilometers of the source. So we should be focusing on the scotopic response when we talk about looking at sky glow. What I'm going to do now is to talk about the brightness of the different light sources. Light sources are chosen based on how much light they provide in lighting circumstances like this, or in daytime or brighter, or fainter somewhat in offices or a living room. This is not too far from a living room. You choose it based on how much energy it produces for your color vision. That may not be the same amount of energy for your nighttime vision. You can see what we'll look at here is a ratio between how much energy or how much light it produces to your cones. That's called lumens, the usual thing we think of when we think about visible light. And I'll look at the ratio between how much light it produces there compared to how much light or how much energy it produces that is detectable by your rods. This is called the scotopic to photopic ratio. And we'll look at it for different lights here. This is how we'll calculate it. For a simple spectrum for low pressure sodium, it's pretty easy. You have pretty much one wavelength. At the scotopic curve, it only has 7% of the maximum response. At the photopic curve, it's 77%. You take the ratio of 7 to 77%, you multiply it by an arbitrary constant, it turns out to be 2.75. You get 0.25. That's the ratio. The important thing to realize here is that you can see as you get from the yellow to the bluer or the broader spectrum lights, the ratio increases. What that means is the scotopic to photopic ratio goes up. That means compared to how much light you see in the daylight, the bigger that ratio is, the more light you see at night as well. The implication here is that the yellow lights are very faint at night, at very low light levels, and the broader spectrum lights are much brighter. Let's take a ratio relative to HPS, which is the most common light source. You can see that all of the LED and the metal halide sources are 1.5 to 3 times or more brighter in the sky than they would be in the room or on the parking lot that you're using them. And on the other hand, low pressure sodium and amber are about 40%. Let's switch the comparison to low pressure sodium. It's just dividing everybody by 0.25 instead of by 0.65. Now you see that compared to low pressure sodium, all of the other LED sources are between almost 4 and 8 times as bright in the sky as the yellow sources are. Even high pressure sodium, a pretty strong yellow light, is 2.5 times as bright, reflecting back out of the sky than low pressure sodium or amber LED. Keep in mind this 8 ratio here for that cool LED, that 5100 Kelvin LED. We're going to go back to that results of that study where we looked at the brightness of the sky as a function of distance. Again, we have distance along the bottom. This time it's just a linear scale, not logarithmic, from basically 100 kilometers to 300 kilometers. And up and down is the brightness of the sky. You can see that that blue LED on the top there is 8 times as bright in the sky as the LED light at the bottom. The LPS light at the bottom. And you can see how the impact of those blue lights falls off more quickly with distance, but they're always brighter than the yellow lights. And dramatically brighter, not a little bit brighter, 8 times nearby, 4 times far away. Thank you, Jim. So what's the implication of all this? Let's start at the bright light levels that I talk about. I'm going to say this room is a bright light level. We choose lights based on how many lumens or how much illuminance they produce, foot candles, whatever units you want to think of, and we balance them to give us the function we want. Let's say we chose, I don't think you'll use the LPS in a room like this, but let's say for a parking lot you might, and you balance them so that they're exactly the same amount of light, the same brightness. Let's say we now move to the faintest level specified in international standards for roadways, which is 3 candela per square meter, 0.3 candela per square meter, and we've started to shift towards that scotopic. We're still doing both scotopic and photopic. We're in that mesopic range. But now we're losing a little bit of that the cone's response, and therefore the yellow light is becoming a little less effective. And you can see that it's dropped 30% from what it started as. Now I went through a lot of trouble with my meter in my office to make sure that that really was a brightness ratio of 0.7 to 1, but I don't know if it shows up in this office. It is actually 0.3 or a 7 to 10 ratio or 0.7 to 1 ratio is kind of hard to see, but that's what's happening. It's just showing that the effect is noticeable at roadway or lighting levels as long as the levels are very low, but it's small. However, when you move to nighttime scotopic vision, it's not small. First of all, you lose color vision entirely, so even the low pressure sodium light looks gray, but it's only 1/4 as bright as the filtered LED reference I used here. Finally, when you look at the sky, you can look at Flagstaff. I'll skip over this one to save some time. This is just a ratio of changing a city from high pressure sodium to an LED to show that even without changing the amount of light, you dramatically increase the sky glow. I'm going to skip over these slides. And I'm going to quickly go, this is a relatively short topic, of instrumentation now, jumping away from vision and looking at instrumentation. The important part to realize here is that we don't have a fixed spectral response that varies depending on the instruments. Astronomical instruments can look at any color of any wavelength of light. Not everyone can look at every wavelength, but there are instruments that will look at all the wavelengths. So what becomes more important in this area is how much of the spectrum are you having to contend with that might have not only your starlight in it, but also the light coming back at you from the ground. How much starlight, how much of that wavelength band, 350 nanometers wide in the visual band, how much of that will be interfered with by different kinds of light? Let's look at high pressure sodium, the most common. It has a coverage of about 65 nanometers in the brightest part. I'm not looking at the very faintest part here, but about 65 nanometers. If you look at metal halide, as you can see, metal halide is not the astronomer's most popular light source. It interferes with essentially the entire spectrum. If you go with the low pressure sodium, maybe that gives you an idea why astronomers like low pressure sodium. In addition to visual people, where low pressure sodium is hardly visible and causing sky glow, astronomers also like it because it's very narrow spectrum and interferes with only about 1 nanometer, much smaller impact. If we look at LEDs, it's an intermediate but still very large number, 250 nanometers, and the filtered LED we talked about is about 205 nanometers. So this is what we're looking at when astronomers talk about the impacts of different kinds of light sources on their ability to observe the night sky and spectrum of the astronomical information coming to us from celestial sources. So certainly from minimizing light pollution perspectives, we always worry about distance and how much light we use. Everybody, whether you're a visual astronomer or a cultural astronomer or a kid in the backyard, or whether you're a professional astronomer at observatory, those are important issues. Professional or instrumental astronomy cares mostly about minimum spectral coverage, and these are the wavelength coverage ranges we talked about, from 1 nanometer wide with low pressure sodium, 34 with amber LED, up to almost 300 with some metal halides. From visual and naked eye astronomy perspective, what you're after is the minimum blue-green content, that portion of the spectrum that the rods are most sensitive to when you're looking at the sky. So then we look at the minimum scotopic brightness, and that's the ratios we talked about before, LPS and amber LED being the lowest, and going up to a maximum of 8 for the broadest spectrum metal halide lights. And that's my presentation there.
I guess we got time for a question or two before we take a break. Anybody? Dan?
Because you used the parking lot little phrase a couple times, and you said that you implied that you were a topic response. I guess in some national parks, particularly Yellowstone, there's been designs that there's not that bright. They're definitely in the mesopic. And so I guess my question is, how would that affect the spectrum of light you would want to use?
I was trying to get back to it on the graphs, maybe too simple, too far back. Yeah, the question is, I had used the idea of parking lot lighting being photopic, I said at some points. I think I may have mixed my phrases and sometimes said scotopic or photopic and sometimes mesopic. I would say in general, parking lot levels as specified by the lighting industry are clearly in the upper mesopic range. Dan asked the question, is in some environments, particularly parks, some lower levels may be used. And if we're still in the mesopic range, and I agree we are still in the mesopic range, and I misspoke if I said photopic for parking lots, although I have to say some parking lots are clearly way up in the photopic, up over 10-foot candles. But anyway, the professionally lit ones aren't. How does that shift it? It's talking to me here. How does that shift the response? As you go lower and lower down the mesopic range and get closer to the scotopic or the rod response, the perception of brightness is going to shift, and it's not going to be simple. The perception of brightness is a complex phenomenon, and you might get different answers depending on how you ask the question or how you measure it. But I would say that the lower levels you go, the more advantageous it would tend to get as you get more and more rod-like in your response, the more advantageous it would tend to get in terms of sky glow to get yellower. But in terms of visibility on the ground, you'd have to think about it. You might get better visibility on the ground with a more scotopic-rich source, but you're going to increase sky glow by doing it. I would say that the ratios in terms of visibility on the ground are usually too small to overcome those large factors I talked about in the sky. Remember I talked about ranges of 8 to 1, 4 to 1, 5 to 1, 1.5 to 1. Those ratios are very hard to overcome just by changing your lighting levels in the parking lot.
Okay, we will have some more Q&A later. It's 22 minutes after the hour. Let's try and take about a 13-minute break and start again at 25 minutes to the hour, okay?
Those of you who haven't yet registered and gotten your name tags, go back out to the front desk and do that on the break if you have time. Thanks.
Welcome back, everyone, to the second half of this afternoon's primer. My name is Jeff Hall. I'm the director of Lowell Observatory. Real pleasure to be one of the sponsoring organizations along with Keystone and the City of Flagstaff. Thank you all for being here this afternoon. Any of you who have not yet picked up the green registration packets, Maddie also has those at the desk. I understand not everybody got those at the outset. So you can just pick those up when you leave at the end of the session. If you haven't gotten it, it's got the agenda, the attendee list, some basic information about the conference. So now we'll turn it back over to Jim for the rest of the introductory session.
Okay, everybody, welcome back. Now, some of the stuff we're going to do here in the next few minutes is a little bit out of order. It's like it may have been good if I did this a little bit sooner, but it'll all work out in the long run, I think you'll see. At the heart of everything we do, and let me back up for a second. There's a lot of different interested parties in this entire process we're here to talk about. And one of the reasons why you come from so many different backgrounds is because you represent those interests. Some of you are lighting manufacturers. Some of you are lighting installers. Some of you are astronomers. Some of you are photographers. Some of you run national parks or manage other public lands. Some of you are from cities. You manage cities. You run cities. Some of you run city lighting maintenance departments. Some of you actually design lighting installations, et cetera, et cetera. I happen to be, my primary business has been designing lighting installations, but I got really interested in the dark sky movement like about 14 years ago. And it's been one of my personal passions is to learn how to do it better. I think that I have a belief that if we all know enough and we all communicate better, we can find solutions that may not be ideal for any one of us, but they may be great for all of us. And I think that's the core of why we're having this conference, is so that we can have those discussions. So Chris has brought us a great description of the manner in which we identify and deal with artificial sky glow. And frankly, I follow Chris's presentations on the web, and I read them, and I think I understand them, and then he comes along and does a great presentation that makes it even clearer. So I want to thank him for that. I kind of knew a little bit about Deborah's material since I kind of get it firsthand on a day-to-day basis. But the fact of the matter is our partnership was based on a common interest in doing the right thing with lighting too. So that's what we're all here to talk about. I'm going to go over a few things fairly quickly. A lot of this stuff by now is stuff we've already talked about. Then I'm going to hit on a few things that represent some of the areas where the industry and astronomy and the environment and everything are beginning to clash a little bit right now. I want to make sure that what I believe are the issues that we are not in agreement yet or we're just starting to talk about, I want to make sure you understand those clearly so you can discuss them over the next couple days. So first of all, we talk about lighting as physics, and people say, well, what kind of light do we get from the sun? And from the sun, if you look at this slide, the visible spectrum is highlighted. What gets to the planet Earth is red, is in the red. So it's the visible spectrum. There's a lot of infrared, which is to the right, and there's a little bit of ultraviolet, which is to the left. The yellow is what actually comes from the sun. The sun's not a perfect black body radiator, what we call it, but it's pretty close. Those little lines, those dips into the red, those represent absorption lines of water vapor and oxygen and carbon dioxide and even ozone. So this is how it all works, the light coming down from the sun. Each color has a different distinct wavelength. And both Deborah and Chris talked about the different wavelengths. This is just a reminder. In theory, we can see all the way out to about 780 nanometers, which would be a deep, deep, deep red, but we can barely see it. And likewise, in theory, we can see all the way to about 400 nanometers, which is very, very, very deep purple, violet, but we can't quite see that as well either. Green in the middle is pretty much what we are the most sensitive to, as Chris described, with our photopic vision. Photopic vision is this curve. Chris had it too. And I just want to point out that the lumen, when we talk about lumens of light, how much light, we measure the raw quantity of light, it's a lumen. Well, that lumen is based on this curve. That's a very important thing to remember, because it's difficult to talk about light and lumens and not talk about human vision. They're intertwined. So we have to be very careful when we talk about light that doesn't involve human vision. We'll get to that a little bit later. Both Chris and Deborah have talked about the human eye, about the cones, the rods, and the non-vision visual cells, as Deborah described them, the intrinsically photoresponsive ganglion nerve cells, the different parts of the eye. So I'm not going to spend a lot of time on that either. But I do want to talk a little bit those things called lumens. How much light comes from a light source is where lighting design and lighting applications begin. How much light do we want to have in a particular, let's say, room? Well, this room is full of fluorescent light bulbs, and every one of those light bulbs is putting out about 3,000 lumens, just to give you an idea. Your basic candle puts out 12.6 approximately lumens. That, by the way, is based on mathematics. I'll show you in a second. The average incandescent light bulb we've lived with all of our lives and may never see again, the 60-watt bulb, is around 600, 800 lumens. That 1,500-watt metal halide sports luminaire that is not only has the spectrum that astronomers hate, but it can produce a lot of glare too. That's about 100,000 lumens. The moon produces 290 gazillion lumens, and the sun produces 3 quadrillion, gazillion, chameleon lumens. All right? Now, the thing you got to remember is that coming from the sun, only a small portion of those lumens get to Earth. The rest of them go out into space. So if you think about what a small dot the Earth is, we're only getting maybe, 1 gazillionth of that. Very, very tiny amount gets to us. It's still a lot of light, and it's a lot of energy on here on Earth and how we live, but that's... So measuring just lumens is handy for lighting design, though, because each light source or light bulb is rated in lumens, and we have a rough idea how much we're going to get out of it. The basic physics, oops, I got foot candles overwritten by the image here. But the basic physics comes from original illumination science, which said that 1 foot from a candle, you would get 1 foot candle of light on a surface of 1 square foot. And all that mathematics worked out very nicely, and so we've used that to this day. Now, if it's 1 meter away from the candle, and it's an area of 1 square meter, okay, then that's 1 lux, 1 lumen per square meter. That would be a lux. So luxes and foot candles have about a 10-to-1 relationship. That's really important to remember today, because the lux is metric and the foot candle is the old English inch-pound foot system that isn't so good for science. So scientists and engineers and others are starting to use lux now instead of foot candles. So, when we talk about doing lighting applications, we put a certain amount of light onto the surface, and we measure that in lumens per square foot or lumens per square meter, foot candles or lux. That's how much lands on the surface. But what bounces off the surface is a whole different animal, because how much light lands there, a lot of that light's going to get absorbed. If it's a black surface, literally all of it will get absorbed, and not much will be reflected. If it's a white surface, the exact opposite. That is reflected is called luminance. Luminance, and Chris mentioned this as a very important concept. So if I put a lot of light on blacktop paving, and I put the same amount of light on concrete, the concrete's going to bounce a lot more light up into the sky, and it's going to appear brighter. It's going to appear brighter because the luminance is higher, and because it's a higher reflectivity, it will throw more light up in the sky. So the reflection of buildings, the ground plane, and everything else is a big part of the physics of this situation we're trying to figure out. How many lux are normal? Well, Chris did a good job of explaining what is normal in the area of outdoor lighting and below. So if you look at this from the standpoint of what's normal to you, you go outside on a sunny day at noon, and you could be upwards of 100,000 lux. Indoors, it's going to be a lot less. But I'm sticking outdoors for a minute. A sunny day in the shade is much, much less. That's one of the reasons why you go there. A cloudy day out in the open. Now, clouds reduce the amount of light coming from the sun. Duh. I think we all figured that one out. And it could be quite a bit. It really depends upon the density of the clouds and all that other kind of stuff. But you can see the light levels are dropping. A cloudy day in the shade is still 100 to 1,000 lux or so. At sunset, even on a sunny day, as the sun starts to set, the light levels, of course, have dropped a lot. And by the time the sun is completely set and as the light levels keep dropping, if you have a luminance lux meter sitting on place you're measuring, you'll watch them fall to 1 lux and then even below. A moonlight, a lot of people think a moon is a lot of light. It's actually 0.1 lux. And of course, as Chris would tell you, that's still pretty bright. That sort of affects your ability to see a lot of things, but at the same time, it's not much. Starlight would be 0.01 or lux, as Chris said, much less, as a matter of fact. Indoors, the light levels are generally lower by day, but at night, we tend to turn them up a little bit. So relative to nature, when we're indoors by day, the light levels are lower than outdoors. Conversely, when we're indoors at night, the light levels are higher than outdoors. As Deborah would probably tell you, this is potentially a bit of a problem. And we've identified at IDA and other groups that I work with and talk with, that television screens, computer screens, et cetera, actually produce a lot of that blue light that Deborah described as would be giving you the wrong time of day. And that's one of the reasons why we're careful about it. We do tend to light streets and different types of streets at different light levels. By the way, you do notice that the light levels in a romantic restaurant might be very close to the light levels we use out on the street. A lot of people don't realize that, but those are the light levels we're shooting for. One of the big questions is, and we'll get to this a little bit later, are those light levels correct? And that's one of the big questions that I want to address as we get to those slides. Chris showed us a scale of what he called the scotopic to photopic ratio. The process at which you go from your day vision or your cone vision to your rod vision or your night vision, that shift is called the Purkinje shift. And what it means is as the light levels drop, you slowly lose your ability to see things foveal, that is right on axis, and you slowly lose your ability to see color. And then at some point, it begins to really totally change and disappear. And your peripheral vision, your rods are mostly in your peripheral vision, and they begin to dominate. One of the interesting things we did this was a mock-up test that we did for some lighting at Yosemite National Park. In a new development of the park, I had developed a concept of using very, very low light levels. The Illuminating Engineering Society, which I'll bring up a little bit later, recommends certain light levels for us to practice by. And those are good things for you to follow. But the standards of the day were for light levels in the 10 lux area lots. 10 lux, about 1 foot candle. That was standard commercial light levels in the day I first started working at Yosemite. And I said, well, that's wrong. It's absolutely terrible. The light pollution, the problems that will be created. And I worked and developed a paper that said it is reasonable to light streets and parking lots and things at Yosemite at 1/10 or less than the IES recommended. Now, this was unheard of in the day. Today, of course, we know better. But it was unheard of in the day. But the reason why I did it was because architects and engineers, and we're going to bring this up a little bit later when I talk about liability, architects and engineers said, well, I'm not going to design for anything less than a foot candle because it's not safe. It doesn't meet standards. And so no one was willing to change and design for less. So I produced a paper, we worked with a design team on a project, and we did it for less. And we did it at much lower light levels, around, actually is under 1 lux instead of 10 lux, which was normal. And we had 45 people, because part of the process I was going through was gathering information on how the public and police and others responded to these much lower light levels. And I can recall standing out there in the middle of a parking lot looking at a bunch of cars, and we're talking about it, and everybody said, well, this is fine. We could see just perfectly. This is great. What's the big deal? And then I said, so what color is that car over there? And they looked at it, and they said, we don't know. Because we pushed the light levels down so low that we were now getting down into scotopic vision where you cannot tell color. It's often said that the job of your scotopic vision, which is your rods, is to protect you. It's to detect things in the periphery and to call attention to them so your eyes will turn and you'll try to detect them with your cones and your on what's called foveal vision. That whole process and how the scotopic to photopic issue relates is all part of the reason why this is so complicated for us to do. Now I'm going to show you some different spectra, because one of the coolest things that's come out in terms of equipment that we use in professional lighting these days are pocket spectrometers. And we can actually go out and measure the spectrum of lights. We don't have to guess anymore. Here, for example, is a spectrum of sunlight. I tried specifically to measure just the light from the sun with very little of the light from the sky, because skylight and sunlight are different. If you block out the sunlight, you get something entirely different. So it's about 5,400 Kelvin, and we use Kelvin to describe the color temperature. This is a very important concept you're going to hear a lot about in the course of the next hour. 5,400 K or 5,400 Kelvin is a light that is fairly neutral in terms of its spectral response. However, when your eyes are adapted to a warmer colored light, it looks very blue. So there is a process in the human eye called color adaptation. We don't know an awful lot about it. But what I know is that if we sit in a light full of very warm colored lights, and then I turn on very cool colored lights, they look very blue. And then you will ultimately adapt. And then when I turn on the really warm color lights, they'll look really orange. This whole process of changing white balance is part of how our eyes do adapt. And again, it's not very well understood or explained. So as we look at this, we say, okay, I get it. There's red, there's yellow, there's green, there's blue, there's cyan, which is a very important, blue-green is a very important color. Blue and then into the violets, and only the blue and violets start to trail off a little bit. To the right is infrared, and there's a lot of it. That's the heat from the sun. That's the radiant heat from the sun. To the left is ultraviolet, which we know has got some good things and some not so good things about it. Gives you sunburns and skin cancer and all that. Now, if I take just the skylight, like Chris described, that Rayleigh scattering that causes light to be scattered by the particles in the atmosphere, it turns out, as Chris said, that it scatters more blue, and so that's why the sky is blue. So you can see that the spectrum we're getting from the sky, it's still a pretty complete spectrum. Pretty much everything is there, but the reds are trailed off a little bit. It emphasizes the blue a little bit more, and as a result, the color temperature is higher. Color temperature, 6,300 K, this does not mean the light has absolutely any temperature to it. It is the color that would be emitted by something called the black body if it were heated to that temperature. The black body is like a piece of iron, infinitely heavy, that won't oxidize. You can heat it to any temperature you want, and the temperature, the color of light it would give off would be that spectrum if you heated it to 6,500 degrees Kelvin. Okay, where are the physicists in the room? What is that, 6,200 centigrade or something? It's pretty, come on, somewhere around there, right? Okay. But variability is normal too, and that's one of the key things we need to, when we talk about health and light and things during the day, as in Deborah's presentation, the fact that light changes all the time. And where you're looking will change too. See, the light from the sky isn't the light that you see unless you walk around like this. The light you see is filtered sun and sky, maybe when you look up like that, but it's going to be filtered through trees, perhaps. Or the bluest sky away from the sun, if you take that one spot in the sky and you look at it, yeah, it's very blue, but it still has quite a bit of red. But if you look at the reflected from the planting area or reflected from earth and grass, you notice right away, well, gee, that's not real blue, is it? I guess maybe reflected from that one planting area, but the other one is, geez, that's 4,800 K. The numbers are getting low, and when K gets lower, the light looks warmer. The point is that I took all these measurements within 2 minutes outdoors at the same spot, just by pointing the meter a different way. So using a number for natural lighting, like 5,000 K or 6,000 K is nice, but it varies a lot more than that. The natural cycle of the sun setting is important too. The color temperature naturally drops from, this was a sequence which ended at sunset at about 6:30, and I started measuring it at about 4 p.m. from 5,200 K to 4,800 K to about 4,100 K to about 3,600 K before plunk. And I couldn't quite get plunk because of where I happened to be standing. The light level goes down, but one of the things you notice is it rolls off more and more and more, with the blue going further and further away. And of course, that's because the sun is coming through more atmosphere and you're getting more scattering. As Deborah pointed out, the moon is not blue. The moon is about 4125 Kelvin, which means it's a fairly warmish neutral source, but the red is still the dominant color. We'd expect that if we took sunlight and shined it on brown dirt, which is roughly what's happening. Deborah made mention of cycles, and these are just to talk a little bit about those annual cycles and how extreme they can be. At the equator, the annual cycle doesn't change much at all. Humans have the same daily cycle year-round. But at Fairbanks or Barrow, Alaska, you have practically no day in winter and no night in the summer, and your body adjusts. So all those human body processes Deborah talked about, we do adapt. And a very simple observation is that jet lag is nothing more than your body trying to readjust to a different time zone. And it takes about a day per time zone to adjust. Windows can change natural light too. And with modern window coatings, they're designed to get rid of infrared, so they also turn down the red a little bit. Now, this is where the rubber meets the road for this meeting, is because when we start looking at nature's light colors, and we start looking at electric light colors, we come to realize they're not very much the same, are they? Fluorescent lamps have been, like the ones we're sitting under, have been said to be very good in terms of light color. Well, there's the fluorescent lamp we're sitting under, pretty close to it, and that's what nature would be doing at the same time with about the same color temperature. There's a lot missing when we look at the fluorescent lamp. Here's another fluorescent lamp. This one's rated to be an extremely high color rendering lamp that is supposed to match natural sunlight. And there's the natural sunlight at the same color temperature. So it really doesn't. And this is one of the first clues we have that from a health standpoint, from a standpoint of other living beings, that the spectra of light source we are used to using, artificial lights, I'll call them that now. I've been spent a lot of my career telling people, it's not artificial light, it's real light. Well, it is real light, but the light source is artificial. And it's about time, I guess, I started saying that. Now, and this is the crux of the issue today, because I'm going to say this today, and it's going to come up 10 times tomorrow morning before 9 o'clock. The real issue we're facing today in all of this is LED lighting. LED lighting is a brand new light source. I've got more slides coming up in a minute about how it works and all that other kind of stuff. But LED lighting spectra is unique in that almost all LED sources have this blue peak, this what we call a valley of cyan, and then a relatively broad band of different colors going through green, yellow, orange, and out into the red. And this looks, again, not an awful lot like nature at the same time, significant differences. How those differences affect us from a design standpoint, from a human health, from the total environment and everything else, in my professional opinion, hasn't been adequately enough researched. We're in a bit of a race to put in, there I go, I told you I wasn't going to give you an opinion, now I do. But we're in a bit of a race to put LEDs into the marketplace. So we're here to really talk about that. There are higher color rendering LED light sources, and this one in particular I want to focus on for a second. What happens with LEDs in the simplest of terms is this blue peak is actually the original color of the LED. Most LEDs are blue. They start out blue, and they convert some of that blue light, or a lot of that blue light, into the rest of the spectrum. And I'll review this again in a minute. Well, if you get a higher color quality LED, it's stealing more of the blue light, and therefore the blue isn't as dominant. And I'm going to show you this a couple more times because I think understanding that relationship is pretty critical in understanding how we can maybe choose better LEDs. Here's the metal halide, and you can see why Chris is not real fond of it, because it's putting out something in just about every part of the spectrum and creating effectively visual noise when you're trying to see a star. Likewise, we look at this is the LEDs that many of the people in the city street lighting programs now say we're going to use this because it resembles moonlight. Well, that's moonlight. I don't think so. So this is again part of the challenge. Another thing I wanted to show you was, and something that hasn't come up yet, is when you normalize the human sensitivity in the different receptor systems, this gets to be real important. The human sensitivity to light with the photopic vision is down here. Our sensitivity of our rods is much greater. I think you can understand it intuitively. The sensitivity of the circadian system is even greater than that. So you can't see these things. Therefore, we're not used to measuring them. But what this is telling us is that, okay, we kind of knew that our rods, our night vision was more sensitive, while our circadian sensors are even more sensitive. So I'm just going to go through these really quickly because we still got a lot of material, but electric light and natural light are a lot different. And we have to be cognizant of that. We don't necessarily always have to replicate natural light. We need to be cognizant of the differences. The light levels that we're used to in nature is a greater range, as Chris pointed out, and a lot different than what we've standardized for designing facilities, both indoors and out. And from a color quality standpoint, there's a number of things. I'm not going to go into details on some of this. Deborah's fairly expert in the cyanosis observation index and some of the other severe defects of color in electric lighting. But the fact of the matter is that the color qualities, the spectral responses and everything of solid state lighting, of fluorescent lighting, and all the electric light sources are far different than nature. The other thing I'm going to throw out there that hasn't been mentioned, but I think is going to be a major issue, is a lot of LED lighting flickers. Flicker we know to be a problem from a stroboscopic standpoint, and it can cause headaches and other problems. A lot of the LED lighting that's out there now flickers, and manufacturers have kind of ignored it, swept that little problem under the rug. I think you go out and buy certain LED lights, particularly dimmable versions, and screw them into sockets in your home, and then wave your hand around in front of them. You'll be surprised how much flicker there really is. So amongst the current light sources, a good phrase that I like to use, and I'll thank my good buddy Chris Monrad for this one, is to refer to most of the electric light sources we just talked about and Chris talked about as legacy. Because we're kind of stuck with them, but we're not necessarily all that fond of them anymore. So they are incandescent lighting, fluorescent lighting, high-intensity discharge, which includes mercury vapor, metal halide, high pressure sodium, low pressure sodium, and plasma. And now we have some old light-emitting diodes, as well as the new ones we might be getting in the near future, and there's neon. Incandescent light. This is a very important slide to remember that incandescent lighting creates a spectrum of light that is basically follows what we call the black body curve. This has been attributed, people have said this is about as natural a light source as we can get. It is quote unquote physically perfect or almost. It doesn't have a lot of blue. It has an increasing amount of cyan, and the green and yellow starts to grow, and the red and orange area becomes very strong. This particular balance, we've learned to say, looks pretty good. That was the original light sources that we used, and we decided we really like this. I think as a lighting designer, if I'm designing a hotel or a restaurant or something, I'm going to find incandescent lights to put in there because they create a quality of light that's not yet been matched. But, they got a pretty good scotopic to photopic ratio too, in terms of creating the light that we think we can see better by. The corollary to it is, as Chris showed us, that might be not, however, the best light source if we want to be able to see the stars. Oh, the other thing is it doesn't have any temperature issues, and it starts immediately, stops immediately, and starts again. It's not always true. Oh, and it's really inefficient. And look at the lamp life. It may last half a year, every night, if you're lucky. How many street lighting departments do you know want to go out and change all the light bulbs a couple times a year? Those days are long gone. So, fluorescent lighting is an alternative. We've started using linear fluorescents, the long tubes like over our heads, in the 1930s. But come more frequently or more currently to the 1980s, 1990s, the compact fluorescent, as in this photograph, started to become the most recognized fluorescent light sources. Fluorescent light sources generate light by they discharge electricity through argon gas that's got a little bit of mercury vapor in it, and that generates a lot of blue and green light, but it generates a lot of ultraviolet. That ultraviolet hits phosphor, the phosphor creates all the rest of the colors, and we get a relatively white spectrum. Modern fluorescence, on the other hand, as you can see in this photo, you see these bands. There's blue, and there's a cyan, and green, and yellow, and orange, a little bit of red. Okay, and these bands are using a principle that was invented in the 1970s of generating narrow band emissions, so we create, in theory, a very good quality white light that is very efficient. Fluorescents stop and start immediately, that's good, but the big problem with fluorescents, other than they need to be a pretty long lamp, the big problem with fluorescents is they don't like to get hot and they don't like to get cold. They have problems putting out the right amount of light output if you do either. They can have an S to P ratio, again from the standpoint of your photopic visibility or your mesopic visibility, that's still pretty high. So again, what we learned from Chris is that number may be good for human vision, but if you're trying to see a truck or a car or a person, but it may be exactly the wrong thing if we're trying to design an outdoor environment for being able to see the stars. Mercury vapor, an obsolete light source, won't spend any time on it, just recognize that it generates yellow, green, blue, and violet, and it's a really awful color. But like metal halide, which was derived from it, these light sources all generate light within that very small area right inside of the tube. That little area right there generates a monstrous amount of light. It's extremely bright. It's called the arc tube. And what happens with these light sources is that inside of that arc tube, temperature and pressure build up. And as temperature and pressure build up, different metals that are inside, metal salts, that are inside the arc tube, which is argon gas, those metal salts ultimately get hot enough and they put their atoms into the plasma that's going on inside of there, and they start emitting different line spectra of light. So each one of those lines is due to a metal that's in the arc tube itself, whether it's a sodium, for example, is the yellow, and cadmium and indium and other metals are what are doing that. So the metal halide light source was wonderful, except it's a high-intensity discharge lamp. HID lamps have one really bad characteristic. When you turn them on, they take about 5 minutes to warm up. If you accidentally turn them off, even for one cycle of the power system, they extinguish the arc and you have to wait 10 minutes to start them back up again. Anybody remember the Super Bowl? Was it the year before last? Where that little problem happened, and we sat there for 20, 25 minutes waiting for a football game to start, and that wasn't the first time it had happened at a Super Bowl either. So this technology has that drawback. Well, here's another reason why that's a drawback. If I'm designing an outdoor lighting system, and I want an outdoor lighting system that has a minimum impact on the environment, that has minimum use of energy, if I'm going to do that, I'm only going to turn it on when I need it. And I'm not going to leave it on all night. But because of high-intensity discharge lighting, we have learned to turn lights on and leave them on all night whether we need them or not. And that's something I think we need to unlearn. Oops. High-pressure sodium has been a more friendly light source for astronomy. It's also been more friendly for city street lighting departments because the lamps last a long time and because they're very energy efficient. But they too are high-intensity discharge lights. But they're pretty temperature insensitive. I would say, and this is just my wild guess, but probably 90% of the municipal street lighting in the United States is high-pressure sodium. All you got to do is fly over the country and look out the window at night, and yeah, that's pretty much 90%. Now, it doesn't speak necessarily to private lighting, like parking lots and tennis courts and all that other stuff. They're going to use our friend the metal halide, because we want the white light. The white light looks clearer and better, quote unquote. But they're all still HIDs. Low-pressure sodium, which has been popularized in the 20th and into the 21st century as being the most astronomy friendly, as Chris very clearly pointed out to us, emits pretty much just that one sodium line. And it enables us to, astronomers in particular, to, and even to the bare eye, which is something I learned from Chris today, we can basically see better the stars at night. Now the big argument is, can we see better the cars at night? And that's one of the struggles we're going through right now. So along comes these little devils, the LED. The original LEDs were like these guys on the left. You know, each little LED inside, there's two wires going in, a negative and a positive. And inside there is a diode, which is an electronic device. We've been using them for a century now. But that little diode, based on the quantum physics of the assembly, gives off a particular color of light. But it's a narrow band particular color of light. So with the exception of the one on the left, each one of those is a fairly pure color, whether it's red or yellow or amber or green or two different types of green. There's a cyan one. We can kind of get within reasonable distance. There's like, I don't know, 8 or 9 or 10 different colors of LED that are pretty common. The one on the left is a white one. Okay, I'll come back to that in a second. On the right, you see a modern LED module. This is actually one of many different types made by Cree. Each one of those little yellow things in there is an LED. Okay, so what they do is they put them all together in an array like this. You can see the little solder pads for the electrical circuits. And then they put them all underneath a lens that gathers the light and sends the light more or less where you want it to go. Important thing to recognize is you see that for the most part, all those yellow LEDs, that yellow color is actually phosphor. And the way LEDs generate light is it starts off as blue, and then it comes out and it hits phosphor. It hits the same type of phosphor, more or less, that fluorescent lamps use. So in other words, the big secret is actually LEDs are little tiny fluorescent lamps. A lot of people don't realize that, but it's really that simple. So why do we like LEDs so much? Well, we look at the energy efficiency. LEDs have now gone past the point where just about any other light source cannot compete. And that's with white light, which is not necessarily as efficiency in terms of lumens per watt, or efficacy is the proper word. They're not quite, well, they're hard to beat. And they're getting better every day. And the expectation is within the next couple of years, they will exceed any other light source we've ever had to work with, save the sun. The life is excellent when you compare it to the life of all of the electric light sources we have. It is as good or better than any of them, for the most part. Now, so there's certain fluorescent lamps are pretty good, but the HIDs can't even begin to compete. Lumen depreciation, light bulbs age. They don't put out as much light, after half their life as they did when they on day one. But with LEDs, this lumen depreciation is manageable, and there's ways to actually improve its behavior. The color temperature or the color quality you want on the LED, what do you want? It's pretty much anything that you want is probably being made now. The color rendering index, which we'll talk about in a second, or color quality, whatever you want, is pretty much being made now. The color consistency from one to the next can be superb. Then again, it can be awful. And one of the major issues early on in the LED industry was being able to sell LEDs so that they matched well enough. So if I put an LED in one light and 12 inches away was another light, that they didn't have significantly different colors, because that would look terrible. So they've done a pretty good job of solving that. Color shift over time. LEDs can shift color. And managing that shift so it's within standard limits has also been one of the real challenges of the industry, but they've been able to do a pretty good job of that. The S to P ratio, I'm saying there can be 1.2 to 2.5. You can get an LED with an S to P ratio of 0.2 to 0.5, which is, from an astronomy point of view, better. So we can kind of get anything we want. And that's what's very exciting about LEDs, is they can do darn near anything that all those other light sources combined could do, and maybe more. This is a modern LED module. Basically, you can, again, when you see that yellow color, you know that is phosphor. The phosphor tends to be yellowish in color because of what it does. Efficiency versus spectrum is one of the first issues. I'm going to go over this probably 3 or 4 times, but I'm here to tell you that the more efficient it is, the more issues we're likely to have with the color it gives off. In other words, the most efficient LEDs, we're probably not going to like the color, and the ones we like the color of are probably not going to be the most efficient. LEDs can be bright. That little thing, which is about, I mean, a dime is a lot bigger, okay? The brightness of that thing is 1/6 of the brightness of the sun in terms of candelas per square meter, for those of you who know what those are. 1/6 of the brightness of the sun. And so you don't think looking at one of those isn't going to cause a little problem? Go ahead and stare at the sun for a couple of minutes and see if that causes a problem. No, don't do it, because it will. You know what I mean. Aiming and camo power. LEDs have difficulty being pointed exactly in a particular direction. The technology, basically, the incandescent lamp taught us a lot of things about optics. And one of them was the smaller we can make the source, the better we can make a reflector of practical size that will direct it somewhere. LEDs tend to get a little big physically to do that. So optical control is a challenge. Replacement or recycling. LEDs use almost exclusively electronics components. Many of them are, by modern standards, extremely sustainable, or at least non-damaging to the environment, which is good. But LEDs require cooling. About 80% of the energy, no, 75% of the energy that goes into an LED becomes heat. 25% becomes light. Now that's about 5 times, 6 times better than an incandescent bulb, but it's still, there's a lot of heat to be gotten rid of. Most LEDs require a heat sink. They're usually mounted to a big old chunk of aluminum. And that big old chunk of aluminum, the manufacture of aluminum, is probably one of the single largest causes of environmental mercury pollution on the planet. So LEDs are not perfectly green. And also, by the way, there's gold in wiring inside of LEDs. And gold is the world's 2nd largest cause of environmental mercury pollution. So when somebody says to you, LEDs are the greenest light source, you go, well, yeah, sort of, but they have their problems. Sustainability is at the core of this. And of course, there's ultimately the value. LEDs are still relatively expensive light sources. And one of the big balancing acts these days is, when do you buy an LED to replace your parking lot light? If you've got a perfectly good metal halide parking lot light system outside, or here it wouldn't be metal halide, would it? It would be high pressure sodium or probably low pressure sodium. When is it time to put in LEDs? Because LEDs' cost is going down while their efficiency is going up. When are we going to get to the point where it's a good time to do that? Well, I can tell you that for conventional lighting, such as airports, Chris Monrad and I did work on the Tucson International Airport. We found that point came about a year ago where it was a good idea to do it, because we're not only able to use a lot less wattage and eliminate a lot of maintenance, which is expensive, we're able to turn the lights off half the night. So all kinds of contributions, good comes from doing that. So let's get down to this. This is one of the core issues we're going to be talking about, is the question of color temperature. These photographs are from the Los Angeles Street Lighting Project, in which the city of Los Angeles has replaced 250,000 streetlights that were originally high-pressure sodium on the left and replaced them with LEDs on the right. And you can actually see in this photograph right here to the right, they only did it this far on that street before they took the picture. And you can see the sodium beyond. This is at the core of some great debate today. What color should we be using to light our streets? And I can tell you that Deborah and I have been working with the city of Davis, California, where we live, on their street lighting program. They went ahead and followed the standards set by the city of Los Angeles and started putting in 4,000 Kelvin, a very sort of neutral white color, and the community went berserk. And it became a community-wide problem because people said, what is with all this bright white light? We liked our high-pressure sodium. We liked our warm-toned light. I had friends in Europe talking about Paris and how they started relighting Paris with 6,500K LEDs that were bluer than that. And they said they ruined Paris. The romance is gone. It's a wrong color. Deborah's particularly sensitive to this. She's constantly reminding me how much she likes those warm-colored lights because they're romantic and they're friendly. And so this is one of the major issues we're going to be talking about in the next couple days. You can find out the color temperature of the light by looking at lighting facts. This is a U.S. Department of Energy program where every LED product is supposed to have a statement like this. It talks about how many lumens are put out by that source, or this is particularly for light bulbs, but there's similar things for luminaires. It says it's a 9 watt, so this is a 9 watt, 840 light bulb, 93 lumens per watt, which is what you can expect from today's replacement lamp technology. The color accuracy of 87, that's a color rendering index. We'll talk about that in a minute. But then it shows the scale. And this scale shows what happens at 2,600 Kelvin and below. The color temperature of the light is like a very, very dimmed incandescent bulb, bordering on candlelight. It's very warm. There's practically no blue light in the spectrum. And it's very cozy and very, very rosy. As you move to about 3,000 Kelvin, 3,200, you start to break out of what we would call the warm white range. You start breaking into the neutral white range. 3,200 Kelvin is the color temperature of halogen light bulbs. I would say I could probably measure it in this part of the room, but I'm going to guess that this room is probably by itself feels like about 3,000 or 3,500. And Deborah's nodding her head. Her eyes are calibrated, so she can tell color. And I'm not joking. She's really good at it. But a lot of that is being influenced by the amount of light being reflected off the wood, though. Now, everybody turn around and look at the back room. And it's a different color, isn't it? That's probably more like 4,000 Kelvin. Okay? So that's the kind of difference we're talking about. If you sit in this room long enough, everything will look normal. If you sat back there and we closed the door and that's all you looked at, it would be normal. But as we look at it today, we realize the 4,000 is in this sort of neutral to bright white range. Somewhere around 4,500K, it really begins to break into what we would call the daylight range, where the color temperature of the light looks an awful lot like natural daylight going through its normal cycles. Natural daylight is a lot bluer and whiter if you've ever tried to compare it with an electric incandescent lamp. So you can get that data pretty easily. The other data is the color quality, or the color rendering index. This system, the color rendering index system, was developed back in the 1940s when fluorescent lamps were first becoming popular. And it was a system designed to tell us the quality of one lamp's color rendering properties versus another. This system has been used continuously since then, and recently it's come under a lot of criticism. So much so that the Illuminating Engineering Society last week issued a position statement that said, you know what, CRI is pretty much dead. We don't know what we're going to replace it with yet, but it's pretty much dead. And the reason why is because it's not very good for dealing with those spiky spectra that we're seeing from LEDs and other light sources. So for the meantime, what we tell our clients is it's still a useful number, and I'm going to tell you that it's still a useful number, and I'll show you how to use it in a little bit. So your basic LED, as Deborah showed you earlier, the sort of the generic standard LED that was really become the first popular ones, tended to be 4,000 to 6,000 Kelvin, somewhat bluish in appearance. That was because this blue was so much higher than everything else and so dominant. The Valley of Cyan reproduced that critical 500 nanometer light very poorly, started gaining in green, so it did a pretty good job in green, started to roll off in the yellow, and the red started to go off. Now in a better one, this particular color right here, 660, that is the peak reflective response of human blood. So when you look at an LED spectrum like this, if it isn't doing a fairly good job with 660, it's probably going to make human skin look kind of terrible. We use this in indoor lighting in particular to try and say, you know, how one is going to look versus the other. There are high color rendering LED alternatives. A lot of people don't know this. The roadway industry seems to be oblivious to this, but it is possible. This one at 2700K, which is very warm, incandescent. This looks lovely. Look at how big the 660 is. It's almost up to the peak. So, you know, humans are going to look probably pretty darn good. All humans. It doesn't matter what race you are. The blue is really reduced, and this is starting to climb up a little bit. This would be 3,000 Kelvin, just a little bit cooler. A little bit different manufacturer using a different blend of phosphors. You can see the 660 is kind of weak, but the 620 and 630 are very strong. And that's a 93 CRI. You can see how the blue is down, the valley's coming up, this bump isn't too big. The perfect incandescent lamp would be going like that. That's what they're trying to emulate that. Here's 4,000K, again, same process, just getting a little bit bluer, a little bit cooler, and 5,000K, even at high CRI, it's going to have quite a bit of blue. So the blending of phosphors to create these different colors is one of the primary things going on in the LED industry today, is to be able to make the perfect blend that gives you great color and high efficiency. A real challenge. Now, that isn't all that's going on with LEDs. Because the other thing that's going on with LEDs is people have been putting their thinking caps on and saying, what are some of those potential problems of LEDs? Deborah identified problems, and the IDA identified biological problems of short wavelengths. Chris has identified, and astronomers in general have identified problems with just about all wavelengths. So, and it would be better for astronomers if we had something like a low pressure sodium, where we had a light source of a relatively long wavelength and only one wavelength. That would be ideal. So what are we going to do? Well, these things have come onto the marketplace fairly recently as legitimate alternatives for us to discuss over the next couple of days. First of all, filtered LED. We can generate white light, and then we can remove some of the colors. Okay, that's the way we've been filtering lights in the theater since electric lighting entered the theater. A gel takes white light and removes the colors you don't want. So why can't we filter LEDs? Another way to do it is to use phosphors, just like in all the other LEDs, but phosphors that create amber light. So the phosphor blend itself is engineered so it creates an amber color. And then there is remember I told you that LEDs can be made so they generate one color of light. What if we had an LED that generated just a narrow band of amber, very similar to the LED, to low pressure sodium? Well, guess what? They all exist. All of these technologies are viable. The filtered LED technology basically, if this is the standard LED source, what it does is it applies a filter to get rid of this. And the resulting spectrum is a warm-colored, slightly greenish-yellow light. One of its big advantages is from a biological standpoint, it eliminates the most biologically active portion of the spectrum while preserving enough of the spectrum right in this region so that you preserve rod vision. Okay? Because one of the battles we're all going to be facing, we're all going to be talking about, is if we take away human rod vision, what's going to happen? Is this such a good idea for us to pursue? This one preserves human rod vision but gets rid of the most biologically active wavelengths. Here's a couple of different versions. This particular company makes a yellow filter pack that fits on a light bar. And by the way, this is way most outdoor street lighting and parking lot luminaries are made. They're made with light bars. So if I want a 1-bar fixture, a 2-bar fixture, a 3-bar fixture, I make it brighter and brighter. This particular company chose to make each one of these little dots is an LED module, like I showed you earlier, and it's got an optic, a lens that fits right over it. And in this one, the filter is in the lens. One of the interesting things that are being done with both of these is hybrid luminaires, where you might order this with 2 bars of amber and 2 bars of unfiltered, and you might order these with half the luminaires with filtered and half not. And the way you change the power and dim between them or switch between them, you can get all different combinations of the color of light that you might have in the environment. So that's filtered LED or FLED. The spectrum of narrow band original sources of LEDs are kind of interesting, and 2 are particularly important. In a narrow band amber LED, the spectrum looks like this yellow line right here. Very, very similar to low pressure sodium. A little bit wider, but not many wavelengths. The alternative, this is this sort of olive line right here. This is called phosphor-coated or a wideband amber. And you can see it has 660 red. It also has 500 nanometer cyan. But for the most part, it has got the same approximate peak as the narrow band amber. 2 alternatives we might consider so that we kind of split the difference. The narrow band amber replacing our historic low pressure sodium, and the wide band amber when we're not quite as concerned, but we're still very concerned. There are a number of luminaires already installed around the world in various places using one of these lighting systems. The experiments are being conducted now to assess their biological impacts, their environmental impacts, and their astronomical impacts. Compared to most of our legacy light sources, all these are significantly better for all of the things we think we know. But the question is, are they that much better? And are they desirable? How might we use them? That's what we're here to talk about the next 2 days. One of the things I want to do, though, is kind of go down the list of all of our alternatives. And you notice that our legacy sources, high pressure sodium and low pressure sodium, are still very energy efficient relative to the LEDs that we have today, especially some of the LEDs that I was just talking about. So there is a trade-off. There's a trade-off in energy efficiency. Why this becomes critical is you need to look at the program I'm going to show you in a minute that the U.S. Department of Energy has started. They've been basically taking out legacy sources, putting in LEDs that are more energy efficient, and the color we get is what we get. And that is an issue for us all to talk about. I was going to do a break now, but because we got started late and I want to finish as close to on time as possible, I'm just going to keep going, if you don't mind. So in application practices, different skills are used to design different types of lighting. Highway lighting people tend to be unto themselves. Street and roadway lighting people are kind of related to them. But industrial lighting, commercial lighting, light commercial, multifamily, residential lighting, landscape lighting, sports lighting, marine longshore lighting, a number of other types, more or less, individuals practice one or two or three. Very few people try to do it all. There's different reasons for that. A lot of it has to do with the hardware, the fittings, the ratings of equipment, how you install them, et cetera, et cetera. Now, this is one of the biggest things that I think I'm going to add to the discussion, because Deborah and Chris basically kind of laid out what are some of our biggest challenges. But what I think are our biggest challenges is a history of standards. These standards have been established over decades of work by a number of organizations. The very top of the list is the Illuminating Engineering Society. I'm a fellow of the IES. I'm very proud of that. But at the same time, the IES didn't give a crud about environmentally responsible and dark sky lighting until about 1999. A lot of lights got put in before we started saying, maybe that isn't such a great idea. Okay, so my society is a little bit behind, but we're trying to catch up. The latest edition of the handbook, issued in 2011, has undertaken to do a much better job at explaining and recommending how to design responsible lighting. But boy, I'll tell you, before that, there wasn't much. There are recommended practices. RP8 is street and roadway lighting. That is a hugely critical document we'll talk more about in a second. RP20, which is right now rumored to be just about the new one just about to be out, is parking lighting. I'll tell you why they're important here in a couple minutes. Another set of standards comes from the American Association of State Highway and Traffic Officials. This is based on IES RP6. There's the document, the current DG6 Roadway Lighting Design Guide. Why this is critical is because most state and local street lighting departments use this as their Bible. If you look at who it came from, you begin to realize, okay, some people took this pretty seriously, and they produce standards. But there's standards from other places too. OSHA, the American Petroleum Institute. I'll reserve my comments for that one. But even from Major League Baseball, the National Football League, the U.S. Tennis Association, and more standards from all kinds of places, from the gas and petroleum industry for lighting gas stations, from the outdoor car retailers. They all have standards, and many of these standards are dated, and many of them are too much, but they're out there. They are standards, and that's an issue. There are codes. The National Electrical Code, of course, is dominant. It says you're going to put lights in so that they're safe. Well, okay, that's not hard. And everybody follows that pretty well. Energy codes, a little bit less well followed, depends upon the state. In California, Title 24 is really enforced, and you have to meet it. Other states, it really depends upon the enthusiasm for enforcing the energy codes. ASHRAE IES 90.1 or IECC are the two energy codes. Energy codes have a good effect. Energy codes, if they're properly written, and these are, basically give you just enough watts to light your parking lot or your driveway or your roadway or whatever. They give you just enough so that you don't overlight them. Okay, if you're going to meet the code, you're probably not going to blow it by overlighting something. So they serve a valuable purpose. Then there's the green codes. The green codes actually came out of U.S. Green Buildings Council's LEED system. And what happened was USGBC said, a lot of people aren't making their buildings LEED rated because they can't afford the cost of LEED documentation, which is pretty high. So these codes put LEED into code language. So the building department enforces it. In California, we deal with California Title 24 Part 11, also known as Cal Green. ASHRAE IES USGBC NCE 189, and the International Green Construction Code. In some states, these codes are going to take a while to adapt. In some states, they're already on the books. That's the way these types of codes go. But from a practical application, if I'm going to design the lighting for this roadway, the things I'm supposed to take into account include the average light level in the pavement, measured in lux, the maximum luminance level, measured in candelas per square meter, the minimum luminance level, measured also in candelas per square meter, the ratio of maximum to minimum, and the ratio of average to minimum. These are the things I'm supposed to take into account. So I use computers to calculate and predict the light levels that I'm going to get. In traditional design, lights, historic lights, particularly our legacy sources, tended to put out pools of light. So it was a big spot of light right at the base of the pole, and then in between the poles there was kind of a darkish area. With new LED light sources in particular, the uniformity is much greater. One of the side benefits from this, and it is a big side benefit for all of our interests here, is that when we do that, the average light levels we use can be much lower. So when we relight a parking lot, say at Tucson International, instead of the average light level of the entire parking lot being 40 lux, so that we can have a minimum of 10 lux, instead we can light the whole thing to less than 20 lux, instead of 40, to less than 20, and probably around 15, because we can make it so much more even. That is one of the major side benefits of solid-state or LED lighting. So when I do the calculations, whether I do them point by point using a computer that gives me the luminance at every particular point along this roadway, or whether I do it graphically so I can see here's a parking lot, and you can see that the yellow areas are brighter and the blue areas are darker, and I can set up the colors so they tell me where I've met or failed to meet the amount. I can light roadways accordingly and take a look at them. The latest technology, this is the latest software, and this software gives me a very good graphic representation so I can kind of see what a good job that I did or didn't do, and intersections as well. We've gotten to the point where our calculations are so good that roadway lighting designers can really, really hit a home run. So if we give them the right tools, we should be able to get the lighting levels down. We should be able to get them down to the bare minimums. There's a number of basic geometric relationships that we also consider when we do typical lighting. Street luminaires, we try to maximize how far apart we can put them. So we like to spread them 6 to 1. In other words, 6 pole heights apart, or better, if we can make it 8 pole heights apart. We save a lot of poles, but we end up creating a lot of glare. Typical parking lot luminaires, again, there's normal relationships, kind of based on parking lot design and bumper rows. So the pole height is really a function of whether you're putting it every bumper row, every other bumper row, or every third bumper row, how far apart you put the poles. Once you start doing a lot of parking lots, you realize this stuff's pretty standard, cookie cutter, you can crank it out. So then, using the computer skills we have today, the modern light sources, you hone it down. So if the standard you're trying to meet says 10 lux average, and by goodness, you're going to be 10.01 lux. You're not going to be 20 lux. You're not going to do that sort of thing if you're doing a good design. So it's a designer's challenge. The designers, that's all the people who are going to design the lighting as a result of everything we do here. First thing is going to be meeting standards criteria. A designer has an obligation to do that. Minimizing energy use and meeting the energy code at the same time. Okay, talk about how you can do some of that, Steve. Meeting other regulations such as ordinances and minimizing maintenance. Secondary considerations for parking lots and roadways and other things are going to be appearance, the off-street glare, and the upward light that you create. They're there, but they're secondary. Luminaire design and shielding. A new rating standard has come out, so if I take a luminaire and I draw a line straight down to the ground, that's called nadir. And that line sort of demarks where the primary light beam that I'm going to use for measurements occurs. The back side in outdoor lighting is away from the street, and the front side is to the street side. Some luminaires are designed to be mounted over the center of the street, but most aren't. The IES has developed this classification system called BUG. BUG stands for backlight, uplight, glare. And it's a classification system that has some obvious and some not so obvious characteristics. What it does is it divides the zones in the three-dimensional space all around the luminaire into, and there's some different names for them. But first of all, there's the uplight, are the zones which are from the horizontal line through the luminaire and up. And it breaks down into two zones. There's a zone that's just, that aqua-colored zone right there, that's just barely above horizontal. Those light rays are going to go through the most atmosphere and probably cause the most light pollution. The rest of them, though, will cause light pollution too. The green is between 80 and 90 degrees, just barely down from horizontal. Those almost always cause glare. Seldom do they do much good. The yellow zone between about 60 and 80 causes glare, but it also allows the widest spacing between luminaires. So manufacturers try and get the most between 60 and about 72, and by the time you get to 80, put out practically nothing. That's part of outdoor roadway fixture design. The red zone is pretty much the useful zone going down. This is where we have stuff. And then there's the backlight zones, the sort of brown area, and once again, the glare backlight and the potential uplight backlight. We separate backlight from front light because most of the time the backlight in street lights is shining in somebody's bedroom window. Okay, so it's pretty important. Or it's shining off property and lighting somebody else's property. So we're concerned about backlight. Backlight mostly creates light trespass. So the backlight low, the backlight medium, and the backlight high are three different zones. The backlight low, it can be useful. Backlight medium starts to get to be a problem, but backlight high is really only useful if you're in the middle of a parking lot and there is no front and back. Uplight and sky glow, again, that front high, which is between 80 and 90, can sometimes cause a little bit of sky glow. But the upper lower, of course, is probably going to cause the most, what we believe, and I'll let Chris correct me on this, probably going to cause the most difficult sky glow, but of course everything going up causes sky glow. Oh, and glare. This is one of the hidden secrets of the BUG system, and the BUG system is an IES official system. The BUG system is a rating system based on zonal lumens, not percentage of zonal lumens, but absolute. What it effectively does is it prevents luminaires from being too powerful for their application. In other words, you can get a luminaire that has the same looking photometric curve, but because it has a higher lumen package or a bigger wattage, might not be acceptable where a lower package might. I'll show you examples of that here in a second. This takes us into lighting zones. The official lighting zones of the CIE, which is the international standard, and the IES now, are these 5 lighting zones. Lighting zone 0, which means rural and wilderness. I think you can guess that the lighting there should be very restricted. Zone 1 is sort of rural and maybe residential. Zone 2, suburban commercial, maybe urban residential. Zone 3 is an urban commercial. And Zone 4 is big-time light. We sort of reserve that for special situations. Lighting fixtures like this one can be rated according to these, and a BUG rating, 223 for this one, is an example. That BUG rating means is that the backlight is 2, the uplight is 2, the glare is 3, and if we were in lighting zone 2, this probably wouldn't be an acceptable luminaire because one of the numbers was higher than 2. By the way, for those of you who are concerned about how much uplight is being created, this luminaire with uplight 2 is generating the total uplight of 3.34 candles. It's not much. They're pretty restrictive. Unshielded lights are uplight greater than 4. They're throwing light up into the sky, forget it. Fully shielded lights are less than 2, sometimes as low as 0. This is the direction we're headed. Fully shielded ornamental lights, this is kind of tricky because this light right here, that's this guy, is shining light down, so you'd say, well, it's fully shielded luminaire. But some of the light is going to hit these black metal parts and bounce a tiny little bit of light up. And so for this reason, these fully shielded ornamental luminaires are a little bit of a photometric challenge. We think we've dealt with it in the bug system, but it's there. Sports lighting is going to be one of the more tricky things to do. The bug system is not designed to work with sports lighting. There's a sports lighting, as many of you know, there's a range from the most unshielded and throwing light everywhere luminaires, some extraordinarily high performance luminaires that really control light pollution. These are an important part of what we'll probably want to be discussing too, because people are going to want to have sports lighting even in some of our most critical areas. Some of the common bad practices of improper shielding, which causes all glare, trespass, sky glow. Lighting when not needed. I'll show you this example. This is Interstate 10 in Texas, and this is Interstate 110 in California. Notice any difference about what's on the side or middle of the road? California doesn't light freeways, except at entrance and exit ramps. Period. This freeway has got 300,000 cars a day. By AASHTO standards, 30,000 cars a day warrants continuous freeway lighting like this. By the way, you see how many cars are there? So you kind of got to beg the question. And I've posed this because I'm going to get to a slide in a few minutes called risk management. You hear a lot of cities say, well, we can't eliminate street lighting. We'll get sued. Well, the state of California said, go ahead, sue us. And nobody's beaten them yet because they said, we save so much money by not continuously lighting freeways, and there is no proof that more accidents occur here than here, or the same traffic levels. No proof whatsoever. So it's a legitimate argument about whether we should be lighting certain streets. Not all streets, but certain streets. Overlighting. This is a photograph Nancy Clanton took up in Alaska. Wouldn't you want to have that kind of lighting in your neighborhood at night? Historic lighting. Oftentimes we'll say, well, it's historic, so we have to do it. No, you don't. We can find decorative luminaires that look historic enough but don't create this type of light pollution. Deborah showed you this slide earlier, but it's, what I really want to do is introduce context. She told you about what happened when they lighted the Sundial Bridge and the impact upon salmon runs. Well, there's all kinds of context situations, the national parks, public lands, sea turtles and ocean fronts. There's all kinds of places where the context is extremely demanding. And we need better language for that, and that language is just starting to creep into the lighting industry. Some of the trends in the lighting industry, and this is one that disturbs me a lot, and it is the Municipal Solid-State Street Lighting Consortium, movement of the U.S. Department of Energy. The goal of this organization is to replace every street light with an LED street light. And their standards right now are to put in the 4,000 Kelvin low color rendering index LED and remove all those high pressure sodiums. And to me, I want to put this on the table, that this is something that can be managed, or we can let it get out of control in the region, because there's a lot of pressure, political pressure, to simply follow the standard specifications of this organization. It involves mostly replacement lighting. Here you can see a replacement lighting system in progress. This is what they did exactly in Davis. Took out the high pressure sodiums, put in, I think it was these guys right here. And one of the side problems I'll tell you about that we discovered is the shielding of these LEDs is not as good as the shielding of the legacy sources in many of these luminaires. So they cause more backlight and more glare. Retrofits. Retrofits are various types of light bulbs that people can screw in, replace a legacy source, and convert it to LEDs. Make it much more energy efficient, save a lot of energy, and we have the same color and now light distribution challenges. Where does the light go? And I can assure you the light isn't going to be controlled particularly well. Even the DOE's, this is from a recent street lighting retrofit where they actually compared the performance of the LED products to the high-pressure sodium products they're replacing. And of course, they always save wattage, but they always reduce the light levels, too. And they put out fewer lumens. They improve the color, but many times, in this case, the uplight rating goes down, but the glare rating goes up from the LED. So there's some question as to how much better they really are. I think it's a legitimate part of our discussion. Another worldwide trend, particularly in France, this is a national law, that thou shalt turn your lights down or off, pretty much. So this is Paris today. And you can see that after hours, certainly, it's a much darker city than it used to be. That's one of the trends. However, there's a contradictory trend in Asia or even in San Francisco, where more lighting is seen as better. This is cultural. There are some cultural issues, I think, in all of our cultures, and it really dates back to the invention of the original gas lights, that people feel that a brightly lighted city is a safer and better city, or people feel that it's a richer and better city. And some of those things are certainly here in Shanghai are epitomize that approach. Mitigation strategies. Here's ways that we have learned we can mitigate the impacts of light at night. Uplight shielding. Well, it's pretty obvious. We've talked a little bit about that. There's a limited number of exceptions where we might not want it. We might want to allow, for example, the lighting of the Eiffel Tower, but we'll turn off everything else. That's a legitimate discussion. Special use permits. Sports stadiums. They're going to create a light dome, and we have to have permits for those. So you're going to do mostly uplight shielding, but occasionally there may be a situation where any standards or codes or ordinances or anything we develop have got to be flexible enough so that communities can still be communities. Backlight shielding. Backlight shielding comes in real handy because when people start putting in these street lights in particular, if they don't have a good backlight rating, they are going to cause trespass into bedroom windows. There are some places where you might want to allow backlight, though. I've come up with the idea of complementary site trespass, where if I've got a parking lot and you've got a parking lot, my backlight on your parking lot and your backlight on mine can help. Or where you trespass from a driveway onto the street, so you can transition the corner better, things like that. Glare shielding, again by zone. Reduce the rating near property line and street, there's a number of ways to do this. The glare shielding, I got this one wrong, those should be G's, not B's. But the idea that glare shielding is going to be, I think, one of, we want to talk a lot about because glare reductions and LED lighting are sort of somewhat at odds. Reducing light levels. I think that there's a number of opportunities for us to use lower light levels. The work that I've done and Chad and others have done in the national parks have shown that a very little light goes a long way in a dark environment. We need to learn to preserve those dark environments by putting in very little light and establishing standards to do that. Light levels by lighting zone and strong policy when not to light. 12 years ago, Nancy Clant and I went to the IES. We're both fellows of the IES. We went in and we looked at the board. We said, damn it, you've got to come up with language in the IES handbook that says when not to light is okay. And to be frank, I don't think the IES has done a very good job of that yet. But we're beginning to get the message out. Spectrum. It is possible, and I showed you LEDs that are like 2700K or 3000K, especially the higher CI ones, have significantly reduced the excessive blue emissions and create more of the warmer light that it's a very pleasant light with a significantly reduced potential environmental impact. But for the more difficult design situations, including developing programs like we have here in Flagstaff. By the way, we're going to run a little long because I want Chris to talk for a few minutes about Flagstaff. But in putting these light sources in are part of the possibilities. Adaptive lighting is another thing that's come up. Adaptive lighting is where we dim lightings by neighborhood, by time of day, by time of year, whatever, and we can dim by the time of night. So dimming lighting systems according to community needs is something else adaptive lighting does. So turning lights off when the parking lots are empty is a really, really good idea. Rosemont Copper is a project that Chris Monrad and I have worked on, where in developing a master lighting plan for the site, compared to business as usual lighting, we're able to mitigate the lighting impacts by well over 60%, actually approaching 90%, measured in terms of lumen hours. Regulatory options, ordinances. Ordinances are developed by cities. Cities can save a lot of time by adopting one of several pattern ordinances, including the model lighting ordinance and the pattern outdoor lighting code. There's also a number of popular ordinances being passed around from city to city. Standards, getting at the IES standards, using the least amount of light. The most restrictive standard is a way to control light. One of the things that we've targeted at IDA is try to get to AASHTO and some of the other organizations and work with them to develop something, I don't know why I did that, something better. Federal highway, state highway administrations, standards USGSA, DOE, EPA, and DOD, and OSHA standards. OSHA standards, for example, require 5 foot candles, 50 lux, on the docks of longshore, ships being unloaded all night long very evenly. Sports lighting standards, corporate standards, state transportation standards, federal highway standards, you get the idea. Codes and regulations, energy codes, building codes, life safety codes, ATM laws. You can't overrule the ATM laws in California. So you have this beautiful lighting installation, and you have this one glare bomb on the side of the building because it's lighting an ATM. And then there's litigation and loss prevention. Everybody's afraid they're going to get sued. There was a very important landmark case in California. The city of Riverside won a suit against somebody who got hurt, unfortunately, crossing the street where there was a burned out street light. They sued the city. The California Court of Appeals said, cities are not responsible for providing you a single lumen of light. That's your problem. So, for those cities who say, oh, we're going to get sued for everything, maybe not, maybe not. Chris, you want to come up now and talk about the exemplary program you've developed here? Sorry, we're running a little bit late, but hopefully we'll get it all fit in this afternoon.
Would you start my second one, Jim? Go for the upper one. So you're quicker. My hands aren't so good. And then start the show. Whichever way you like.
2 from the beginning. Okay.
Thanks, Jim, and I apologize, everybody. I know this is getting probably a little warm in the seat. This is brief. I think it won't take me 10 minutes. I'll try to make it shorter. All I want to do is briefly give a summary of a lighting code with a track record and some basic ideas of how and why it works. There's some differences about the way it's been developed, which I think are crucial as we move forward and think about light pollution management in the future. And I mean light pollution management in distinction to lighting management. Briefly, I'm going to give a little bit of history. In fact, this is all of it right here. Flagstaff adopted its first lighting code of any kind, addressing lighting impacts on the astronomical environment in 1958. We think this is the first one in the world. It was very simple. It just stopped searchlights. But it was the beginning of an idea. I'm going to focus the rest of the time on the current code, which was developed in 1989, where we developed the first spectrum, lumens per acre, signs, and lighting zone standards. Thank you, Todd. We're going to talk about light pollution management that is used in these codes, using the lighting zone, shielding spectrum, and limits per acre standards. And we're going to talk about how we have made it effective at accomplishing its goals through the KISS principle and continuous involvement. So, in 1989, somebody wanted to locate a 24-hour, 7 days a week, 365 days a year trucking facility 1.5 miles from the Naval Observatory. We didn't know what to do. We just said this didn't seem like a compatible use. We made that argument at the Zoning Authority, and we won, both through the Planning and Zoning Commission and the Board of Supervisors. So it was turned down. Then we had a question from the developer. Okay, you said that there's too much light here. Tell us how much isn't too much light. That was a difficult question. That was a question we didn't expect. Developing an answer to that question is what developed our lighting code and the way it's written. The important thing to realize, though, is it's based on an analysis of lighting conditions and expected impacts from lighting developments in the future. It's a light pollution management code. We came up with these 2 bullet points here based on, I don't want to go into those are long. We have 2 or 3 lighting zones, lighting zone 1, 2, and 3. In lighting zone 1, we determined how much light could be allowed per acre based on the number of acres we expected to be using that light per acre to give no more than a certain brightening of the sky at the Naval Observatory. 30% was the number we chose. 30%, by the way, for many observatories would be considered a devastating impact. But that was the number we chose based on our proximity to the city, the existing of zoning already in place in the area of lighting zone 1, and that's the number we based it upon. The lighting zones look like this. For I'm sure local folks, this is a familiar enough map to see what the city of Flagstaff looks like, but you can see on the left side of the screen a couple of concentric circles, which are centered around the Naval Observatory, which is what I was just talking about. The lighting zone 1 was based on 25,000 lumens per acre and was based on, let's say, the impact of a development right there where the yellow freight facility, the trucking facility, excuse me, was to be located at the end of that arrow 1.5 miles. By the time you got to the boundary of 2.5 miles, the impact of a yellow freight-like facility, because of that increasing distance and the fall off of its impact, would fall to 1/2. So at that boundary, we doubled the lumen per acre limit to 50. And then further at 7 miles, it goes to 1/4 of the impact at 1.5 miles. So the limit was doubled yet again to 100. These are based on the original idea of managing light pollution at the Naval Observatory and not necessarily on how much light somebody might need to develop an acre of land in any of these lighting zones. These standards look like this in the code. I don't want to get into it much except to indicate that's where the numbers appear. There's something to keep in mind here that it's also a very strong spectrum management code. It requires the use of low pressure sodium for most outdoor lighting. From other studies I've done, the kind of lighting where what is sometimes called Class 2 lighting in lighting codes, which is described as general lighting like for roadways or parking lots, where in some circles it might be said that you don't need color perception in that area. You have color perception provided by other sources such as headlights, or you don't particularly need it, or at least it's a trade-off that you can get better spectrum management by giving up color perception. So my experience has shown that Class 2 lighting is about 80% of the outdoor lighting we do in this country, at least in the Flagstaff area. So we require that you use low pressure sodium for that. That's the minimum spectral impact. We allow non-LPS lighting at a 10% level in most of these zones, and that's based on a general idea that some people might have some white lighting they'd need, uses they would need, such as at entryways, where there would be an argument. You might be able to want to read the colors of signs, or you might want to be able to stand and talk with somebody and be able to tell, at least by convenience, what color their clothes are. You may not necessarily need to know, but you might enjoy that. It's also based on the idea that, a more complex idea or subtle idea that mixing a little bit of white light with pure yellow light actually doesn't take very much before you gain a lot of color perception back. The room will still, if we lit this room with low pressure sodium lighting and then put 10% fluorescent, the room would still look very yellow, but all of a sudden you could tell the colors of people's shirts again. It'd be very yellow, but you could see the red, blue, and green. So that 10% is based on that. Keep in mind, this table has 15 numbers in it for all of Flagstaff and Coconino County. That's going to come up here in a moment. The other shielding standards I just want to point out are quite strict. Fully shielded is required in almost all applications. The amount of unshielded lighting allowed in decorative lighting you see there on that table and also in residential lighting is also capped, although that's in a footnote and I didn't want to list that here. Why do we believe it's effective? And I'll talk in just a second, my last couple slides, to show about how it has been effective. We think it's important to keep it simple. We pointed out here that there are 15 and 18 standards, which is 33, I believe, to reflect the standards applied for shielding and for lighting amounts in all three zones. There are some additional standards. I list 6 here for special standards for service station canopies in terms of how much light they can have. There's a couple other standards, odds and ends, like for sports fields and here and there. But basically, the numbers are meant to be kept small to make it manageable. So people aren't confronted with a building code, which is, somebody here working in the building department? How thick is the building code? It's a couple inches, right? Okay, we're trying to keep it lower than that because we know that at this stage in our culture, we only get lighting codes if we keep them simple. If we try to get them complicated, even though it may be justified someday by our society's perspectives or priorities, it isn't there yet. So we've got to keep it simple or it's not happening. These standards are all confirmed before construction, so people don't have to go out with lighting meters and find out, oh, you put that light in the wrong place, and by the way, the concrete's already set. None of these require anything more sophisticated than doing arithmetic, adding up numbers of lights, adding up numbers of lumens, dividing by numbers of acres. It's all arithmetic. Results. 2 papers have been published on the studying Flagstaff's impacts. I was involved with both of them, although I wasn't the only author. In 1999, at a conference, an International Astronomical Union conference in Vienna, I published a paper where I had measured the brightness of Flagstaff as viewed from those satellite images you've seen of the world at night. And I compared it to other cities. And I find here in that paper that the integrated brightness of Flagstaff, reading the quote there, is approximately that of an average town of about 37,000, or 67% as much as an average city of its size. Seems to be working. Another paper published just 4 years ago or 5 years ago where I studied all of the lighting in Flagstaff along with several co-authors, one of them in the audience here, studied Flagstaff's, did inventories of lighting in Flagstaff and looked at how lighting had changed after the adoption of the 1989 code. Parcel by parcel we looked at lighting. And the conclusion is that the adoption of the 1989 lighting code has reduced the growth of Flagstaff sky glow from an expected 43% increase based on the parcels that had been developed since 1989. Without the code, it would have been 43%, and we had just a 17% increase. There are many examples in Flagstaff of lighting sites that have been built under this standard. Many of them quite prominent. You will see some of them if you attend the tour tomorrow night, drive around, you will see the Flagstaff Medical Center. An IDA, Lighting Award winner, by the way. IDA, Scott is here from IDA. There are many national franchises which are building under these standards, including low pressure sodium, including lumens per acre limits. I don't want to go into all of them here. This is just a small sampling. And it's important to realize that after 25 years of experience, though the lumen per acre caps were driven by a sky glow management goal and have achieved that goal, the numbers were expected to be and have proven to be workable for lighting needs. There was quite a bit of legwork done when we were talking about these standards, 25,000 lumens per acre, 50,000, et cetera, to try to see what are people actually out there using before we have any standards. How much light are people using on sites? There was quite a bit of research done. There could have been done more. I mean, it was only one person doing it. But nonetheless, we felt they were reasonable, and they have proven to be reasonable and workable. Designers may have to think outside of the box more often than they're used to. Many lighting designers, and I'm sure Jim and Deborah could attest to this, are not used to being told that you can't use just as much as you want. They're not used to that at all. So they have to think twice. But it's been shown, I think it's shown that we've got workable levels here. Many other areas have adopted codes based on the Flagstaff code or the pattern outdoor lighting code, which Jim referred to, which is similar. The conclusions I want to draw is that most lighting codes are based on lighting practice standards, and Jim has referred to these as well, with no overall assessment of light pollution impacts, thresholds, or targets. In this day and age, that probably has to be true because we don't know enough about light pollution impacts, although that's improving. Thresholds, there's not much known about that yet. How much light in my bedroom is going to be a problem? How much isn't going to be a problem? What are the spectral impacts? There's a lot that's not known yet, and I don't think that light pollution management is a reasonable goal for all lighting codes. However, I think it should be a standard that we look to for the future. More areas should be considering light pollution management as a part of what they're trying to do with their lighting codes. Flagstaff bases codes on the light, sky glow assessment and the management target. It has worked for 25 years. It has produced measurable success. It nonetheless requires continuous involvement by city administrative and enforcement staff, many of whom are in this room, and I am continuously thankful to all of them for the work and the relationships we've developed over 2.5 decades of working on this and making it work. The elected officials, and I don't know if any of them are here tonight, but they've all over the years collaborated and supported as well. Astronomers and dark sky advocates. It's a continuous process. There's more information on this at this website if people are interested in looking into more about the Flagstaff Lighting Code. And that's it.
Thank you, Chris, and I also want to thank Jim and Deborah again for their presentation. So that's one more time. So just a couple of quick logistics about this evening and tomorrow. So you all know that that the reception is from 7 to 9 this evening. The reception is actually being sponsored by the International Dark Skies IDA, International Dark Skies Association. So we're grateful for that. It's at the Lowell Observatory. It's there's a map out on the table as you're walking out the door that has the map of the campus, and the reception is in the Rotunda Museum. But what you need to do is to park in the parking lot that's in the front of the building, and then walk in through the visitor center, and then the visitor center people will guide you through that building, and there's a walkway to get to the rotunda. I'm assuming that everyone knows how to get to the Lowell Observatory. Anyone not know how to get to the Lowell Observatory? Oh, wonderful. Okay. One more thing. Those of you who have either posters or exhibits need to be over to the High Country Conference Center, which is where we're meeting tomorrow, between 5:30 and 7 this evening to set those up. So we have a little bit of a crew and staff over there to help you do that if you need to do that. I think that's it. Hopefully we'll see you all at the reception, and if not, tomorrow morning we have a continental breakfast at between 7 and 7:45, and we're starting right at 7:45 a.m. Thanks.